بسم الله الرحمن الرحيم والصلاة والسلام على أشرف الأنبياء والمرسلين سيدنا محمد وعلى آله وصحبه أجمعين. Ladies and gentlemen, good morning and welcome to the first AJSE Symposium. AJSE is the Arabian Journal for Science and Engineering. It's my honor to have you all here as we gather to explore the latest advancements in AI transforming systems and engage in meaningful discussions that pushes the boundaries of knowledge. First, I would like to extend a warm welcome to our distinguished speakers, experts, researchers. Your insight will inspire, challenge, and enrich discussions throughout the event. I also to express my gratitude to KFUPM administration, especially to the Vice President of Research and Innovation, Dr. Ali Sheikhi, for his continued support to AJSE and to this symposium. Special thanks also go to the scientific committee, the KICS team led by Dr. Fahd Zahrani and the AJSE office staff. This event would not have been possible without your dedication and hard work. Thank you. As we come together, we have an opportunity to explore critical fields such as energy and sustainability, smart cities and electrification solutions, cybersecurity, digital systems, and high-performance computing, and engineering processes for complex systems. These topics are at the heart of today's global challenges, and the insight shared here will help drive real-world solutions. This symposium is not just an academic gathering. It's a platform for collaboration. The connections made here have the potential to shape AI-driven advancements across industries and communities in Saudi Arabia and beyond. As for AJSE, in 2024, we have marked 49 years of continued publications. And in 2025, we will celebrate, inshallah, the 50th anniversary of the journal. In 2024, AJSE proudly sustained its Q2 ranking. In brief, from 1975, the year of inception of the journal, to 2006, the AJSE impact factor was below 0.1. And the number of submissions did not exceed 200 per year. For comparison, in 2024, we recorded an impact factor of 2.6 and around 14,000 submissions. So we are targeting an even higher impact factor. Impact factor is not the target, of course, the quality. And hope to move to Q1 within 2 years, inshallah. Once again, thank you all for being part of this symposium. We look forward to fruitful discussions, fresh perspectives, and meaningful collaborations. Now, I would like to invite Dr. Ayad Zahrani, Assistant Vice President of Research and Innovation, to deliver the opening ceremony. Thank you.
شكرا دكتور بسام. بسم الله والصلاة والسلام على رسول الله. Assalamu alaikum everyone. Good morning, ladies and gentlemen, and welcome to the inaugural of AI Transforming Systems Symposium, the AIST. This gathering today brings together experts and researchers to explore how AI can address critical challenges and shape practical solutions through research and innovation. Organized in collaboration with the Arabian Journal for Science and Engineering, AJSE, this symposium demonstrates our commitment at KFUPM in advancing impactful research and fostering collaboration across wide disciplines. At KFUBM, we firmly deem research and innovation are the driving forces behind meaningful transformation. Our commitment to advancing knowledge is reflected in the strategic initiatives of our research centers, which serve as hubs for interdisciplinary collaboration. These centers, mostly of interdisciplinary nature, bring together experts across domains, breaking traditional boundaries to tackle complex challenges and with integrated solutions. In this direction, the AITS Symposium underscores the importance of this approach as it encourages dialogue that bridges diverse fields and perspectives. AI, while still an emerging tool in our systems, holds immense potential to address pressing issues in areas such as intelligent urban systems, renewable energy technologies, sustainable environmental practices, and almost every other strategic sector. To harness this potential effectively, we must prioritize the integration of research efforts, ensuring that our collective expertise leads to impactful outcomes. Previous experiences indicate that the success of AI in transforming systems depends on fostering a culture of collaboration, where disciplines converge not just in principle, but in practice. At KFUBM, this ethos is reflected not only in our research centers, but also in supporting entities such as the AJSE. As the host of this symposium, the AJSE provides an avenue for researchers to share insights and explore interdisciplinary ideas, particularly in emerging fields like artificial intelligence and sustainable engineering. By curating focused discussions and connecting researchers with a global audience, the AJSE contributes to our broader mission of driving innovation and producing knowledge, meaningful knowledge that addresses pressing challenges. Its role, while complementary, demonstrates the collaborative spirit that defines the symposium and KFUBM's vision for transformational research. This symposium is not only an opportunity to share knowledge, but also a reminder of your shared responsibility as researchers to truly harness the potential of AI through embracing joint objectives that transcend individual priorities. By forcing partnerships and aligning our research efforts, we can ensure that our work contributes meaningfully to Vision 2030 and position KFUBM in leadership in a leadership global position. To leave you with a final thought, I extend my heartfelt gratitude on behalf of Dr. Ali Sheikhi to the organizers for their meticulous planning and to the participants for their invaluable contributions to the discourse and collaborations at this symposium. Your efforts in fostering interdisciplinary research and driving innovative solutions have been so far instrumental in the success of this symposium, and without doubt will continue to shape its legacy. Without further ado, I would like to hand the floor over to Dr. Bassam Al-Ali. Thank you for joining the AITS Symposium. I hope you enjoy the symposium sessions. And have a good day, please.
Thank you, Dr. Ayad. I would like to invite speakers and organizing committee and everyone would like to share with us a photo, please. Okay, can you please come over for a photo, please?
Please, you can stand up and get closer for the photo, please. Okay, thank you again for coming, and I would like to invite Dr. Tariq Sheltami, please, to introduce the keynote speaker.
Assalamu alaikum. Bismillah, sallallahu alaihi wasallam. I would like to welcome everybody to the symposium. Today we'll have the first keynote speaker, Dr. Ghassan Al-Ragib. The title of presentation is Computation Visual Explanation. That's a case study in robustness, uncertainty, and interoperability. Dr. Ragib, or Professor Ragib, is currently the John and Birlu McCarthy Chair Professor at Georgia Tech in the lab of Omni Lab for Intelligent Visual Engineering and Sciences. His group is focusing on robust, interpretable machine learning algorithms, uncertainty, and trust advancing AI across various real-world applications. I would like to welcome Dr. Ragib for the presentation. Dr. Ragib, please come to the stage. Do you need a mic or is something?
Assalamu alaikum. Thank you, Dr. Tariq. Thank you, Dr. Bassam Al-Ali, all the organizing committee. Thanks, KFUBM, for hosting. It's very bright here, so I don't see your faces. It's always good to come back to my alma mater. I was joking with one of my classmates that we are the senior people now in the room. So I don't know, that might be a good thing. Okay, so how do I advance this? Okay. Okay, so today, yes, this is good. What about now? Okay. It's always good to see some of the students who are in the exchange program. Some of them come to Georgia Tech for 1 semester. I saw Al-Aqsa this morning, so really good to have others who are here haven't met yet. So let me get into it. So I'll talk about explainability and mainly visual explanations. So let me start this by looking at this. This is SAM, Segment Anything Model, that Meta released in 2023, like in mid-2023. This is basically trained, a segmentation model. It trained on 11 billion data points. So it's very, very, very heavily trained model. You can see basically this is data coming from their paper. If you look at this, basically segmentation is a very, very tough problem. Segmentation meaning what? You mean every single object, the background, the foreground, the trees, the cows, and so on. You can apply it to medical as well, right? So it's a very, very, very heavily trained foundation model, very, very powerful. So where does it really work? If you look at those who are really into Cityscape autonomous vehicle applications, this is Cityscape. Cityscape for each frame took people 90 minutes to label even one frame. So SAM or SAM2 can be extremely powerful in doing this segmentation and this label generation. Even it's weak label, but still it's very, very powerful. However, so far it's all good. Foundation models are really very, very powerful. However, if you go to this example, and all the data that I'm showing and the results in here are really coming from our own code that are open source. If you look at this one, so how does really SAM work? You as a user, you will prompt. What is your prompt? You have two kind of points. You have to include inclusion and exclusion. Inclusion meaning what? Meaning that this basically points, what you have in the green in here, that means these are really part of the object if you really want to segment the bat, the baseball bats. And the red ones, basically these are the exclusion points, right? So now what you see in here, you have basically 3 different ways of how you can do the inclusion and exclusion. What you see on the right-hand side, this is averaged over many data points, 200,000 prompts on 6,000 images. This is part of data that we released recently called point prompt. If you are interested, you can see the QR code in the upper right corner on 16 different data sets from biomedical all the way to natural. What you can see in here, like B, C, and D, the performance basically really drops. So the performance drops. So basically there is a trend where humans over-prompt, meaning that they start really well, and then if you add more inclusion points, more exclusion points, and then things will become deteriorating. And you can see on the right-hand side there, if you look at the exclusion points, we have the red ones, one on the pants and the one on the grass. That actually gave you even worse results, right? So now there is this over-prompting that's really happening in these foundation models. So there's this interaction between the human as a prompter and these foundation models that have to be basically taken into account, not only trial and error. What we have seen so far, and maybe you have experienced that in ChatGPT and other foundation model, when you are really kind of interacting with them, things may not always improve over time. Okay. So now, what I come to this one, basically, there is always a discrepancy between what you are hoping for, you have wishful thinking, what in reality you get, right? So usually you have these foundation models, they are very powerful. For a certain specific applications, they really work extremely well, but once you deploy them in the real life, then things become really not as robust. So what I'm looking at in here is that how can these foundation models, how can any model can really deal with novel data? What do I mean by novel data? Novel data mean something that really unexpected prompts. This distribution is different. There is a shift in distribution. There is some noise. Maybe somebody would like to attack your data. So all of these are novel data. And this is an autonomous vehicle data that we created many years ago. And Dr. Mu'taz maybe was part of contributing to this data generation, where basically you have 17 different distortions for autonomous vehicle come from environmental, like weather, or like dirt and noise, or some kind of compression into the sensors. So how can really foundation model react to this novel data? So let's look at this. What people have been doing is really looking at how we can really handle novel data during training, right? So let's really look at this toy example. And this data actually came from, or this graphs from autonomous vehicle applications. Let's look at the first one. What we have in here, we have 2 classes. We have the gray and we have the blue, right? So this is the representation space. If you look at the top one, if you start your training with those are in the red circle, so these are really very far from the decision boundary, right? So this is what? This is the easy ones, right? These are the low information, right? So very quickly you have your decision boundary. If you look at the samples in here versus the performance, you see basically this is the curve, right? You very quickly you have doing very good job, As you have low information, you start from the easy samples. As you go training, you will get really improving in the results. What about if you start with the tough ones, right? You start with the difficult examples. What are the different examples? These are the ones very close to the decision boundary. Those are the ones that you can confuse them with each other. They can be class 1 or class 2, right? If you start there, you can see basically your decision boundary, you start with really very bad performance, very low quality, and that's what you have in here. You have the high information. It will take you a while to correct and go there, right? So now, what's happening in here, if you start with the most novel aberrant sample should not be used in the early training, right? That's kind of the output from this experiment. So okay, let me use these basically later on in the training. What will happen, and this is the real examples, you have the epochs, you have the performance, you have MNIST, and you have fashion MNIST. MNIST and fashion MNIST are a little different in their distribution. If you start basically say, okay, I would like to handle my data later on, or the difficult ones, you have very well-known phenomena, catastrophic forgetting, meaning that whatever you start training on, you will forget about at the end of the training, right? And that's really very challenging. So now, what you have, this novel data basically is very tough to train on early on, is also very tough to train on at the end of the training, right? So where do you handle in the training? What I'm really trying to convey today, and I hope this is one of the messages that we are trying to, what do you do with novel data if you cannot really figure out where to handle them in the training? So let's look at this example in here. This is real data. Again, this is segmentation. Again, using the SAM, for example. What you have on the left-hand side in here, if you look in here, I have one exclusion, one inclusion points. In the green, that's inclusion. In the red is the exclusion. What you see, you're segmented basically the cat extremely well. This is a very good segmentation, above 80% in results. What you have in here is uncertainty, right? And uncertainty, what you have, blue dark region means very low uncertainty. That means if you look at the face of and the head of the cat, you have very low uncertainty. That means you already have very good confidence. So this is really amazing results. On the right-hand side, you increase your inclusion points and look at the performance. Basically, the performance really deteriorates. You really missed most of this hand, the arm in here. And uncertainty basically there is extremely high. So now, what I'm trying to convey in here is not only the performance will deteriorate, but also your uncertainty, how certain you are about your finding is also a problem. Okay, so the first message I would like to convey, and I'm hoping the next half an hour, you really are, at least you are motivated with this. We spend a lot of time on data collection, like we spend a lot of time on that, optimization, training. What I'm really trying to convey that we have a lot to do at inference, right? Inferential machine learning, I think is really worth working on. And there is a lot to be done at the inferential machine learning, not to spend too much time on the training or the getting data from the source. Now, the second message is that inferential techniques can be analyzed via uncertainty estimation. And I hope that at the end I will come back completely full cycle to this idea. And then finally, uncertainty and explainability is basically the two faces of the same coin. Explainable research, or XAI, is nothing but uncertainty estimation. Actually, it's for those who really work on these topics, you will see basically the math at the end of the day is basically equivalent. And I'm hoping to convey this message at the end of this presentation. So what is really explainability in this case? If you look at explainability, I mean, there is a very well-known YouTube channel, basically on the Wired channel on YouTube, where basically you convey the same message, depends on to middle school, to high school, to college students, to adults, to experts, right? And this is the same content, same information, but the way you are conveying, basically, or explaining it is different. It depends on who your audience is, right? The same thing in machine learning and AI and XAI. We'd like to have achieved something very similar. So let's look at this example in here. What I have in here, this is very well known for those who really work on ImageNet. This is very famous image in ImageNet. This is the bull mastiff. This is basically the label for this image. Now, what we are looking at in here, can we really kind of, convey and explain what's really happening in the image? So, for example, if you look at, these are all very true output from XAI models. If the question is why bull mastiff, then the answer will be this. The darker in the red, that means these features in the image were used to really classify this image as bull mastiff. And bull mastiff is the correct breed and the correct label for this. So in this case, it's really the face, the jaws of the dog basically are really highlighted. Now the next question could be something like this, which is a counterfactual. what if bull mastiff was not in the image, right? You can tell the model, what if the dog is not there? So how do you, what next is in, you can really label. And in this case, it makes sense to have the cat, right? So if there's really no bull mastiff, then the next thing I'm looking at is the cat. And then finally, you have another one which is called observed contrastive, which is why bull mastiff rather than a box. Now, bull mastiff and boxer, basically these are two breeds of dogs. And they're really, really kind of, they are different in a very, very small detail. And if you look at this is a true output from the model. The model basically figured out basically there is this very, very small feature that's really differentiate two breeds of dogs. And you never really kind of trained the model to differentiate between them, but the model really understood and figured out the difference between them on its own, right? Of course, that's one thing which is very, very promising. But if you look at this, there is confusion with the cat, which is really good. I mean, that means the model is really kind of, has some knowledge to explore. So now, this kind of the explainability that we are really looking at today. So now, the question is, so if that's the case, then where does really context come into the picture? And the context come into the picture depends on who's really asking the question, right? So you can have explainable model. If it's a policymaker, a decision-making entity is really asking the question, then the purpose is different. If it's somebody you try to learn, that's different. So if you have this model, and all of these are really true output from this model. This is spoon pill, right? If a kid is really asking why spoon pill, you have the model in here. This is the output. The output is really highlighting the body, like like that pink body. You have feather. Then basically, it's really learning. So the purpose in here: can you explain a decision to this kid? If somebody who's an expert, right, and then asking the question, now they have very fine-grained differences. If you look at the output in here, why spoon pill rather than a flamingo? The model itself figured out the difference between a spoon pill and a flamingo is the S-shaped neck. This is the true output, right? So now you can see in here, it's really highlighting the neck is the difference between the spoon pill and the flamingo. And the model really figured that out on its own, right? So now in this case, I'm making an assessment of this model for my purpose as a scientist. Another one will be, what if, why spoon pill rather than a fox, right? I'm trying to figure out, cannot really differentiate between a fox and a spoon pill, like a very, very different entity. And if you look in here, almost everything is highlighted, the body, the neck, the beak, and so on. So now, maybe one conclusion could be, I really should have trust into this model. So the way you ask the question, it will really relay context and relevance to your explainable model. Okay, so I have 3 parts to talk about in this case. Then the first one, I will talk about how can we really explain AI models using some intervention from the human beings. The next, I will talk about robustness element, and then I will go back all the way to uncertainty at the end of this presentation. So all what I'll talk about in the next 10 minutes or so are really in this Signal Processing Magazine special issue paper, if you are interested in looking at this in much more detail and the math part of it. So for those who really do explainability, there is a very de facto XAI model called GradCam. So GradCam, this can work for any model where at the end you have a convolutional neural network or convolutional layer. You work on the convolutional layer. Basically, you backpropagate your class. If I am backpropagating YC, which is the correct class in this case, you backpropagate, and then you take an average pool, and then now you multiply each one of those activation functions, basically with the average of that. And then now you have these activation functions, you apply a ReLU to them, and then now you have this heat map because you're expanding. So now, this is what you'll get output. And then you convey this on top of this, you'll get what I showed you earlier, right? So in this case, the bull mastiff face will be. So this is very, very well known. The key I want you to look at, what we are really backpropagating in this case is the correct class, is YC. YC is the correct class. So I'm backpropagating the correct class and trying to figure out features in the input space that really were used to come at this conclusion. This is very well known GradCam. So if you look at this, I'm trying to figure out, can I use the same GradCam as it is without really too much changes to really answer these questions? And actually what I just showed you is this question. GradCam is really answering the question of why P or why bull mastiff, the correct question. Now, if I backpropagate the negative of that, right? I'm taking the negatives in here, or what I do, just have the negative in front of it, then this is a counterfactual, right? I'm saying, what if not bull mastiff, right? And I do everything is the same. Nothing really changes in the GradCam. And now, next one, I really backpropagate the cross entropy between the correct class and another class. Like if you have 10 classes, for example, you have bull mastiff, you have boxer, for example, you backpropagate the cross entropy between the boxer and the bull mastiff. Then all what you need to change, everything is the same. You can just change basically what you are backpropagating, which is the cross entropy or the Jacobian between the P and the Q in this case, right? So if that's the case, then this is what you will get. You'll get basically the Jow's part, that's the difference between the P and the Q. The P is bull mastiff, the Q is the boxer, and then you have some confusion with the cat. So what I showed you in here, basically, we can use these cases, and I want to showcase some of the examples. What I'm showing you in here, you cannot see it, okay. What I have in here, in the first column, I have the original image, I have the grad cam, I have my contrastive image 1, and here I have my contrastive image 2, and then I am showing you basically what the grad cam is showing. So if you look at those cases basically in here, what is the difference between flamingo and spoonbill is the S shape, right? Difference between a boxer and a bull mastiff is really the Jow's part. What's the difference between don't turn left and don't turn right is really showing basically exactly what you have in the middle in here. All of these are human interpretable, meaning that we can still, the explanation makes sense to us as humans. So there is an agreement between the human and the AI model about how they arrive at this conclusion, right? If you look at the next, these few in here, what is the difference between bull mastiff and completely a different bird image of a blue jay? It's completely the same as grad cam, right? Because completely different objects. So in this case, yes, I'm expecting a completely no change in my grad cam between the two heat maps. Let's look at this case on here. If you look at this case in here, I'm telling the AI what is the difference between don't turn left and the stop sign, right? If you look at what it's highlighted this the left bottom corner, right? To us as a human, what do you expect? You expect what? You expect the AI model to tell you there is no STOP, right? There is no stop sign or there is no line and so on, right? However, the model is telling you what? I decided the difference between a stop sign and don't turn left is this portion here, right? This was to us basically, okay, this is something is not right, right? There is something wrong with this AI model because it doesn't make any sense. You can't really explain this because of the left corner, the bottom left corner of this sign. And then what we did, we looked at the training data. So this is the training data for the CURE TSR data set. And if you look at the data, it turned out the stop sign is the only one among all of them that basically have a diagonal in the lower left corner. Given that the neural networks are very, very lazy ones, they are amazing at having shortcuts, right? So they figured out the difference between don't turn left and the stop sign is this line here. It doesn't have to bother itself with STOP or anything else. There's a shortcut. I can differentiate between the two using this feature. I'm good, right? And that's where the trust in AI becomes an issue, right? Because they are amazingly designed to optimize, which means what? Get to the solution as soon as possible, right? In a quasi-optimal way. So it did that. So the XI didn't really do anything wrong. It did what we trained it to do, but it's not really makes sense to us to differentiate between the two signs using this kind of feature. Okay, so that's basically to lay the ground of how we can really get this explainability. I will talk next about trust and uncertainty. However, if you are really interested in talking about how all the math behind complete explanation, in this paper what we show is that you can get a complete explanation using 3 questions. One of the form basically YP, the other one YP other than Q, and why not P. 3 questions will give you a complete mathematical explanation of any AI model. Okay, let's look at the robustness piece. And this from this paper back 2 years ago in Europe, if you are really interested in explaining this in more detail. Look at how we as humans see things. So if this is from computational neuroscience, they have a model how we humans look at things. The first thing, there are 2 stages. There is the first stage is sensing. We as our human vision system, we sense things. We look at things when they have some features. We look at edges, colors, objects, and so on. And then without us realizing, we have a reflection phase. A reflection means that we are really asking the questions. We ask questions without us realizing to really understand what's really happening in the scene. These questions, for example, if you are looking at this image, then the question that we could ask, why is spoon better than flamingo? Why is spoon better than a crane? And so on. So we have a lot of questions basically we can really ask ourselves. That's really the reflection. So now the question becomes, can we can we mimic something like this in a neural network? Right? Can we have a visual sensing stage followed by a reflection stage, right? And the answer is yes, we can do that, right? And then the question becomes, how can we formulate this? How can we set up this layout in here, right? So what is our goal? Our goal is really to have this simulate introspection that happens in the human vision system into a neural network pipeline. What's the definition in this case? We define introspections as answers to logical and targeted questions. Now the question becomes, what are these questions that we can really ask in our reflection? And actually what we showed, because of our earlier work, you have only 3 questions, will give you a complete explanation. Then basically we can really ask these questions. Like these are reflection questions, these are contrastive questions. So it could be something of the form, why P rather than Q? Why bull mastiff rather than a boxer in this case? So this becomes, can I really have this definition? And I will just skip through this detail. So what we did is the following. I have my model. Again, I'm a big fan of don't spend your time trying to retrain things from scratch or even fine tune unless you have to. So give me a model, doesn't matter what architecture it is, it's already trained, right? So now I have this model, and then remember when I showed you basically you back propagate the cross entry between P and Q, the distance between them, right? So imagine you have 10 classes, right? So now I have an input image, I have an input data for my architecture, and then I backpropagate the hot vectors, right? I backpropagate 0, 1, and then zeros, 0, 0, 1, all zeros, 0, 0, 0, 1, and then all zeros, and so on. So I have 10 of these backpropagations, right? Now, these are the contrastive features. So now I'm looking at contrastive, not to explain, but as features. So now, each one of those, when I backpropagate, I look at the gradients. These are the gradients. I take the gradients from the last convolutional layer. This becomes my feature. So for each sample in here, I have a feature, right? What we showed in the paper, you don't really need to do 10 different backpropagation. You can do one backpropagation. All ones is equivalent, right? So mathematically, you backpropagate a hot vector of all ones is the same as you backpropagate hot vectors, 10 of them, with a 0, 1, 0, 0, and 1, 0, 0, 0, and so on form, right? And the math basically in the paper. If you do that, so now what we do, we backpropagate a vector of all ones. You look at the gradient in the last layer. You take these gradients, you normalize, and you make them a vector. Basically, you have now a feature that describe the contrastive feature from this network to this input. And you do that for every single image that you have or single data that you have, right? So now you do that. What you have now, you have, if you have m data points, then you have one feature vector for each one of those m points. And now you input this to a very, very shallow MLP, very small network, you can train it, right? This is the only training part that I'm showing in here. You train on these contrastive features, right? Now, if you do that, the question, what is the advantage, right? So now you have this model, somebody trained it for you, is doing classification or segmentation, and now we added another reflection stage after, which is this reflection. Another question, how does this improve the performance, right? Because again, in the humans, we mimic this idea of basically I'm sensing, I am reflecting, right? So now this one in here is sensing, that one there is reflecting, right? So let's look at some examples of some applications. So the first one is robustness. If you look at these data sets, for example, where you have the same image with many different kind of noise, you have Gaussian noise, defocus noise, Gaussian blur, fog, snow, brightness. The same thing with traffic signs in here. You have a lot of different kind of distortions, right? So now, how does this really improve, right? So let's look at this case. So there is something, you look at papers, we are very clever in academia to make claims that are not very true, right? We just say accuracy is very high, right? We say, but we are hiding 10 other things that are not working, right? That's how we write papers, right? So this is the same thing in machine learning and AI scale this by 1 million, right? Everybody has higher accuracy. The problem is that the deeper the network, then the gap between your confidence and your performance increases, right? So we measure that using calibration error, right? So when somebody tells you, I have a deeper network and I have this performance, ask them what is your calibration error, right? What is your expected calibration error, which is the gap between your confidence and your performance. So look at this example in here. Let's focus on the one on the left-hand side. So I have expectation calibration error. I have performance accuracy. What I'm aiming for, to have very low calibration error and a very high accuracy. So I want to live in the upper left corner of this graph. That will be the best way or the best place for me, right? So the left one is trained on Cypher 10C. Those are the images I showed you on the left-hand side in the previous slide. And then I have different networks. I have Resident 18, Resident 34, Resident 50, Resident 101, and these are for Transformer, also the same performance. So now, what is the difference between these and these? These ones as Resident 18, 34, 50, and 101 as they are. This one here, after introspection, after we add that stage with an MLP, with basically the introspection features as we train that very, very shallow MLP afterward, right? So now if you look at all of these points, those ones in here are showing here, here, there, and there. These are before introspection. After we add that very small reflection network, which is a 2-layer network afterward, all of them move to the left and to the above. The accuracy improved on average 4%. The improvement in the calibration error is 42%. So now what this means that these questions of why P rather than Q is helping the network to make the right decisions basically about the confidence gap between the accuracy and the confidence, right? Or the calibration gap, right? The same thing if you have Cypher 10 with the Cure. These are 17 distortions. Those are 6 distortions over there. It's the same thing. We move to the left and to the top, which is basically improve the accuracy, and we improve the calibration error by 42% and 44%. So we really improve robustness by just looking at how we can add a reflection stage for any trained network. So this is a plug and play, right? You just add this to any network, and then in inference stage, and then it will improve your calibration. That means what? I improve my trust into the model in this case. We apply this for many different applications that are in the paper. We have 17 applications where this really fits. Augments, for example, is very, very well known for robustness. It's very powerful. Our case, basically, we are not really it's equivalent. However, in the calibration error, we improve by 40%. Same accuracy performance, but the confidence or our trust into the model improved by 40% in this case, which is a very, very famous robustness mechanism. And all by just adding that very small step at the reflection stage. If you are interested, there are 17 other applications in the paper from a quality assessment and so on that will really kind of help you understand what's happening there. The last thing I want to talk about is uncertainty. This is called voice in the IEEE signal processing paper. Let me jump into it. Okay, let's look at this case. Again, you'll be experts in the dog breeds today. Okay, so we have Weibel Mastiff, right? So we got this image before from the grad camp, right? But now, each one of those explanations, you have an AI model, it decides this is a bull mastiff. Now you apply explanation, it will explain to you why it's really deciding on this to be this class. And then you have uncertainty about the map itself, right? So what this means, this is bull mastiff, this is why, but in here it means I am really uncertain about the snout, right? The snout region, I'm very uncertain about. I'm not really sure about that, right? And maybe some other parts in the dog body, right? So now, that becomes extremely, extremely important. So how do we evaluate this? What people have been doing in the XAI, you have an image like this, right? You basically start to apply basically kind of a mask, right? Apply just a multiplication. So this is the mask, show this body. You show it in the trained model, you get the class, and you keep doing that. You keep doing that for many different, you can see there is infinite number of combinations of masks that you can apply, right? You can keep doing that. And then you say, okay, on average, if the expected value of my class output for the second mask is always, or on average, above the other expected value of the class for mask 2, that means this mask in here is much better. That means this mask in here is a better mask than this one. That means my explanation, this model is better than that one for my explanation. That's kind of the general evaluation that people have been doing for explainability in this case. Now, so we do the composition, right? This is the details actually in the paper, but it's very simple. What you have in here, you look at the predictive uncertainty. Basically, this is the variation of the output class given an input explainability. And then you have a decomposition between the variance of the expected value and the expected value of the variance. This is very like a variance decomposition standard procedure in this case, right? So now, if what is your role to explain a model? To explain a model, you say you want to get the same class regardless of my mask, right? In a way, you're trying to make the first one, the variation of my output, right? Variance of expected value of y given a mask, it's always have to be 0. I don't want to change my output, right? It's always have to be equal to a 0, right? So in a way, what we are really saying in this case, that visual explanations are really evaluated to always basically reduce the predictive uncertainty in a neural network. We're really trying to make that first term is always a 0. That's how we do it, right? That's why we are trying to push it to do that. What about the second term? The second term is the residual, right? This is the residual part of it, which is basically the expected value of the variance of y given an xx. All the other parts that really could contribute to this class or could really confuse this conclusion, right? So all the other residuals, right? So now the question becomes, what are these other ones? In this case, it's very obvious. Basically, we have some other part, the snout part. We have some of the body of the. So how can we evaluate that one? How can we really measure these things? So if you start to look at, I can pick 1 pixel, right? That's one mask. 2 pixels, that's another mask. I have all the combination of 2 pixels, so it becomes infinity. So you have almost like a huge number of combinations of masks that will really be the residuals, that will confuse the model about this class or basically, or give you the wrong answer. So for the second term. So how can we quantify this? How can we measure this? How can we make a model out of this? What we try to do is, why are we really worried about all the different combinations, right? If you have a classification problem, right, you have 10 classes, all what you need to worry about is the other 9 classes, right? That's all what you need to worry about, which means that the second term, the variance of y given as x1, I can basically name these as depends on the other classes. So y1, y2, all the way to the yn, or y9, or y10 in this case, given the different maps or different masks in this case. So I went from this almost infinite combinations of possible masks to really kind of a finite number of those. So now each one of them will give me, this is one, this is the second one, this is the third one, and so on. Each one of them will give me a certain heat map. So this will give me the residuals that will confuse the model with this classification. So if all what we have in here is the same, this is a trained model. This is what we get basically to get all these Jacobian and the cross entropy between the different classes that we have seen at the very beginning. And then in here, I have these different one. I have maybe n of them. I have 10, 100, 1,000 for ImageNet. And then I take the variance among all of these. I do the variance. That will give me basically the second heat map that I'm looking for in this case. And now what do I do with that? I start to do a kind of evaluation, right? So the next one is just very, very quickly. I will just, before I conclude, how you can evaluate XAI residuals? Really to answer these questions. The Swin transform, for example, is really better than a VGG 16. Is a grad cam better than a grad cam plus plus? And there's many, many different questions you can ask using this methodology. So 2 very quick things. Very simple. You can really do an intersection over union between the different maps. And I will not go through the details, but basically IOU among the different maps will really give you a very, very good measurement. And the other one is signal to noise ratio, right? Signal to noise ratio between the different maps. And this is for us in signal processing. We love signal to noise ratio. It makes things much, much easier, right? Dr. Zakobin and Ali are smiling. But I will not go into the details of how we can do that. But really, bring all of this, just 2 metrics, IOU intersection, signal to noise ratio, will give you basically all what you need for this evaluation. Okay. So before I conclude, I want to really reinforce certain messages. First one, it doesn't matter how much training data you have, right? At the end of the day, there will always be a novel data that you cannot account for, right? Now, people spend a lot of time, a lot of money to train models on this novel data. Good for them, that's good. But I'm trying to really kind of convince you there is a lot of work to be done in the inferential side of things, right? So now, because novel data, either you have a catastrophic forgetting, right? Phenomena, and if you start with it, it basically becomes even more challenging to train your model, right? So that's one. The second one, for robustness element, it doesn't really matter how robust your method is. Somebody will always come with an adversarial attack that will compromise your model. This is something anybody who does really in the security side of things for machine learning, it has been really, really tough because I'm very sure many of you saw the example of having basically, you have an image, classify it as I don't know, the correct class with a confidence of 50%, 90% accuracy, and then you add Gaussian noise. For us, a human looks the same. The performance basically becomes really much is wrong, but the confidence of the network becomes 90%, right? So, and this is challenging in these models. They are super confident in themselves, right? So when somebody has really very limited knowledge, they become very super confident in what they are doing, right? So the same thing in your network, just like any human. So the robustness is an element, is a very substantial challenge if you keep tracking that. Again, this one, I think I'm hoping this kind of an image, this meme will be stuck in your head, that basically I need to work on the inference side of things, not on the optimization only. And then this is something, we have a lot of papers, and Dr. Mu'taz is very familiar with those work, where if you train a model really, really well for an application, whatever the application is, anomaly detection, segmentation, then the knowledge acquired with the model is way more than what it was trained for. It's way more. And we have a lot of papers proving that. There is a lot of knowledge, and if you just apply it to what it was trained for classification only, for segmentation only, you are really limiting yourself about accessing that whole knowledge, right? However, accessing that knowledge, it needs quite a bit of work. You need math, understanding what's really happening, and we believe we have this explainability and uncertainty quantification give you the 1 foot into this knowledge space that you don't really usually see in these models in this case. And again, explainability and uncertainty quantification. I know those who really work on uncertainty for the last 30 years, they don't like this, but I think it's the same thing, right? There is uncertainty element to it, and there is explainability. And I think the math at the end of the day is you can really draw some parallels between the math equations in the two cases. Uncertainty, we have other works where uncertainty comes from your labels, right? Especially for computational imaging application like medical, there is uncertainty about your labels, uncertainty about the data because of the noise, and uncertainty in the model itself, right? And then you can really have some parallel between explainability and uncertainty in this case. I want to thank my team who are really kind of doing the work. I'm just traveling and talking, but they are really the one who really kind of do all the derivations, all the coding that I'm presenting in here. Before I conclude, especially for those who are really students in here, we have more than 15 tutorials recorded with all the content and the codes. These are CVPR, Neural's Big Data, Triple AI, short courses and tutorials online if you are really interested in looking at these. And in conclusion, I want to thank you. If you have any Q&A questions, I'm willing to answer.
Thank you, Professor Hassan, for the presentation. I'm just curious to know if uncertainty affected by the type of noise. Is it best for example, Gaussian noise, for uniform, for how is it affected?
So, yeah, very good question. Thank you, Dr. Zarqouini. It varies a little bit. It varies, but what we showed, even the simplest, even you just add Gaussian noise, and you as look at the 2 data points, as a human, you can't differentiate between them. It's a very, very simple Gaussian with a sigma of 0.00, like it's very, very, very small added. That will really trick the network, right? Different model will react differently, right? But in general, even a simple noise like that will make a big difference in how in the robustness and the uncertainty piece. So, but it's a of it. If you look at distortion on the lens, for example, dirt on the lens, like if you have a camera and you have some dirt there, that will make it very, very tough compared to a Gaussian, for example. But overall, any distortion will make a big difference in these cases. You're welcome.
Thank you, Dr. Hassan, for your nice presentation, very informative. I have just a few questions.
Yes.
I think you were hinting to some fact is that maybe we don't have to spend a lot of effort and computation in deep learning and so on. We have to maybe simplify a little bit the training, use maybe simple neural network But after that, we have to do more steps. And I was thinking that maybe this more steps, we can as well do them using reinforcement learning, the concept of reward and so on. So we train a simple network, maybe as you mentioned, few layers, but then after that we let it train on new data, and then with reinforcement learning maybe we can improve the different KPIs, accuracy, uncertainty, robustness, and so on.
So thank you, Dr. Ahmed. Just a very quick correction. I think still you have to rely on a deep network. I think that the knowledge acquired by a deep network that's trained, you don't really have to spend too much time to come up with a new architecture. If somebody trained Resident 101 or SWAN transformer or any other, foundational model, take it. I think replacing it with a shallow network is not a good idea. What I showed you is you take that model and now there is a lot of knowledge. How can you access that knowledge, right? So one way is just look at the gradient. So one of the things that I would like to, for reinforcement learning, whatever you are backpropagating, doesn't matter what hat vector is, look at the gradient in the last stage, which I showed you in the reflection piece, right? Those gradients, the difference between activation function and gradients, which you can use in the reinforcement learning. Activation function tells you the distance, like how much gradient tell you basically the distance and in which direction. And that's extremely powerful, right? It tells you basically how much the model has to change distance-wise and direction-wise compared to this activation. And then it will be very, very useful for your reinforcement learning cost function.
Thank you very much. I have a follow-up question on this.
Just one more.
Okay. Regarding the conditional variance equations that you mentioned, when you presented this reminded me, as well there are in statistics, like say, approaches to minimize the variance. Can we apply those techniques also there to benefit from, let's say, existing knowledge?
Absolutely, and this is where I'm coming from, right? I'm coming from the background where basically things, I don't like the idea of having a closed box where you don't know what's happening. As you have to understand what's happening, and we have very small techniques like we show, and this is just decomposition for the variance is an example. In the paper, we have a whole derivation of how this very simple decomposition, but it really gives you all what you need to understand what's really happening in that AI model. Absolutely, and the signal to noise ratio idea, the same thing. I think there is a big hype, but also we have really kind of solid knowledge that we can really apply in this case.
Thank you very much.
You're welcome.
Any questions?
Thank you very much, Doctor, for
welcome.
the presentations. It was really excellent. My question is about the time of execution of this algorithm to get the appropriate decision, if this is what I want or something else.
It's as inference. It's as if you are applying it, deployment in real life. So So this is basically kind of, if you look at some of the plots in here came from a project that Ford Motor Company basically deploy in their track, the autonomous vehicles. So these are all of our work. We are not really trying to do anything heavy for the training side. The MLP is the only training that we do, but everything is really happening at the inference. So I'm a big fan of, running things in the inference, get the gradients out, and then do some magic with the gradients, and then all of this is happening in almost real time. Yeah, thank you.
Okay.
First of all, thank you for nice presentation.
Multi-layer pattern, yes.
Although I don't work in the area of artificial network side, but I use some of those models. Recently, I am sure that you are aware of the Lucy in France. The Lucy was taken down because of the catastrophic mistake. So how we can avoid such type of catastrophic mistakes when we are doing the training and also we are doing the testing as well as reinforcement? How we can avoid such type of catastrophic catastrophic outcome, what happened with Lucy?
Thank you for the question. There are many, many questions. There are many, many cases out there, right? Some of them we hear about, some of them we don't really hear about, right? I can tell you from our work with autonomous vehicle companies, they take our codes and their engineers run them on the track, right? And there's a lot of cases, like for example, as simple as having snow on the side of the road will make the autonomous vehicle basically kind of, go completely offside. So
trust in AI is extremely very important, and there are many different ways of how you can really get to the trust. Right, explainability is one of them. Uncertainty is another one. Right, empowering the network to know when it doesn't know is extremely important. Right, are we there yet? I don't think so. I think we have a lot of math that is really missing to make the network aware of its shortcoming. But there's a lot of work being done in that regard. Yeah.
Okay. As long as more modeling is involved, modeling has two components as the regression part and the error part. In the error part, we have two components. One is called lack of fit, and another is called pure error.
Yeah.
The pure error comes from the system.
Yes.
So in the normal machine learning models, we don't have any algorithm to get the ratio between pure error and lack of fit.
But we have uncertainty quantification for the model and the data. We have two separation.
As a total.
Yeah, but we are having algorithm to separate them. Actually, there's a third component which people really ignore in the machine learning, which is the label itself, right? People really assume, for example, for labeling, this is a dog, this is a cat, this is an airplane, this is easy ones. But for autonomous vehicle, for medical imaging, for example, for seismic imaging, you need to go to segmentation where even just off by 1 or 2 pixels, you are missing the tumor, for example, in a machine learning, right? So there is a label uncertainty. And there is a shortcoming. I can tell you in the literature, basically, people are not really accounting for those. And the other one is what you referred to, having everything together, like have these components and how they interact with each other, right? How they interact with each other is very, very important, which we don't have much of work yet on this. But I know that there are some papers are coming out that are really kind of addressing this issue. If you look at ICML submission that were like 2 weeks ago, if you look at the pool of the papers, there is a lot of work just on this problem. So I'm thinking by 2026 we'll have a lot of work in that area.
One last question.
Professor, thank you. I will keep my question short because it was very interesting. You mentioned during your presentation something about backpropagation, which is a very interesting concept. And since you mentioned also the application side of it is also, for example, autonomous vehicles that you were working with, how do you ensure that the relevance is maintained, the relevance of the context is maintained in terms of the ones while you're doing this backpropagation without inducing extra noise, because environmental factors are much faster and they are changing quite rapidly, right?
So there is 2 elements for backpropagation. There's the backpropagation that's really being done in the optimization for in the training. The backpropagation I was talking about, you are not changing the model. All what you are really doing, you're just like at the last layer, you backpropagate in the inference stage. You backpropagate and you take the gradients from the last layer only. And all what you are doing, you make these as features. So these what will tell you, basically if you say an image of a car, right? And you say it's an airplane, right? So now if you take the gradients of the last layer only, if you backpropagate a different label, which is an airplane, it tells you how much the model has to change itself, the manifold, how the manifold will change itself at distance and direction-wise in order to accommodate that this is an airplane label for a car image, right? So you can see the discrepancy between the two, right? So it's the backpropagation in this case is how much the model has to change itself, how much the manifold has to deform to accommodate this kind of a new concept, which is this is an airplane, not a car, right? So it's the backpropagation in my case is a little bit different purpose of the backpropagation in the training, which we are referring to.
Yes, thank you.
You're welcome.
Okay, with this we conclude the
Thank you.
Thank you very much, Dr.
Thank you, Dr. Tariq.
Come back at 10 o'clock, inshallah.
cloud check.
Cloud check. Cloud check. Hey, 1 2 2.
Okay, sound check. Sound check. Test, test, test. Sound check. Sound check. Sound check. Test, 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 test. Sound check. Sound check. Test, test. Come here, come.
Cloud check. Hey, 1 2. Hey, 1 2. Cloud check. Cloud check. Hey, 1 2. Cloud check. Cloud check. Hey, 1 2. Hey, 1 2. Cloud check. Hey, 1 2 2.
Mic test. Check.
Assalamu alaikum wa rahmatullahi wa barakatuh. I would like to welcome you to the session. We have 3 speakers in this session, inshallah. The first talk will be by Dr. Manal Assaf. Dr. Manal, she will present AI from ambition to reality. Dr. Manal has a PhD in computer science from George Washington University. She led major AI projects, including Allam, and her focus is in digital diversity, digital delivery, data-centric AI, and engineering innovation. We'll have Dr. Manal.
Assalamu alaikum wa rahmatullahi wa barakatuh. Thank you, KFUBM. Thank you, Dr. Bassam, for inviting me. It's an honor to be here today with all of you to talk about an AI journey from ambition to reality. I'll talk a little bit about myself before we move to the journey. And back 10 years ago, exactly in 2015, I actually made the journey from academia. I was a PhD student in George Washington University to industry. So from academia to industry since 2015, I joined Microsoft Power BI in the cloud and AI headquarters in the United States. And I worked for Power BI AI features. If you ever used Power BI, Q&A, even before large language models, it was expert system based. I worked on that group. And 3 years ago, after COVID, I moved to Saudi Arabia. I'm originally from Saudi Arabia, so I moved back to Saudi Arabia, and I worked in the National Center of AI. It's part of Sadaya, where we developed Allam and Sautek and a lot of AI products. And now I'm working at Worley, which is an engineering consultation company specialized in the energy sector here in Saudi Arabia. It's an Australian company, international, but I work in this region. So in my talk today, I'll start by a learning moment. This is a culture in engineering companies, especially in oil and gas. When they start any presentation, they spare 2-3 minutes to talk about something not related to the topic, but it's related to a learning or a safety moment for the people. Then I'll talk about AI ambition in Saudi, AI reality in Saudi, and then the journey in the industry. For today learning moment, I would like to speak about the evolution is the only change happens actually every day. Evolution is the only constant happening every day. Change is the only constant happening every day, actually. So if we reflect back with the scientific facts, for years, scientists believe that the Earth is flat and the planets are rotating around it. But then new theories in science like Galileo and Newton, with all the principles it comes with, proved that the scientific, some observations scientifically are not true, and the Earth is not flat, and all the planets are rotating around the sun. So similarly with AI, people are using interchangeably some terminology here or there to explain, especially in industry, to explain an AI, BI, they always mix between these two. And even with an AI, people are not very aware, not like in the scientific community like you, mashallah, but they are not very aware about what's the difference between reinforcement learning, deep learning, you name it, large language models, small language model, and you name it. So the idea here is the definition of science is changing. The definition of even in the large language models, like today, GPT performance is better than yesterday, but it's what the worst would be for the future. Like today, all other language models, they are getting better and faster because they are exposed to more knowledge every day. So it's changing every day. What do we believe today is correct? It could be subject to a change any minute. And from actually my speech today title, and from this learning moment, I will spare 2 minutes to talk about some personal story here. Back in 2017, I was senior engineer in Microsoft Power BI in Seattle, and my sister was a JD student in University of Richmond. She called me one day having a class, research class, and she wanted us to co-author a paper together for that class. The paper title was The Terminological Challenge in Patenting AI. We did great. We wrote a very nice paper. Unfortunately, that paper never published. I wish I publish it now, but anyway, we never published that paper. She got an A+ for that course. And in the conclusion for that paper, we said we kind of have an ambition about having an AI model that can find the context similarity between any two patents, just such that we can figure out if there is any terminological challenge, overcome the terminological challenge in patenting AI. At that time, I was working at Microsoft, and I know one very good architect in Microsoft, data and solution architect, spent more than 30 years in Microsoft, has more than 50 plus patent. In Microsoft, they give you a marble cube if you have a patent. So his disk was full of marbles, you know. So I took that paper, very happy with what I wrote with my sister, and then I gave it to him, asking him for feedback for that paper. And I still quote his comments on that paper. He said it's very nice, well written, very nice paper. But in the conclusion, you said you are looking for an AI in the future to find the context similarity between patents, two patents of AI. And we are decades from that. That was in 2017. We were living in the GPT-3 era at that time. No one even imagined that we are now in 2025 and we can have two patents for ChatGPT and we will find all the similarity between them. And I was in top of one of the giant companies that invested. 2 years later, Microsoft invested $1 billion in OpenAI for GPT-3. We took GPT and we tried to put it in all the project. So it was very ambitious, vision at that time, which today we live in the reality of it. Less than 5 years later, ChatGPT is out in 2022. So when we talk about AI, this is the base where AI is moving. It's very, very fast. What we know about today could be not relevant a year from now, not even 5 years from now. Having said that, I'll move to the AI ambition in Saudi Arabia. If you live here, or you are from Saudi, or you are visiting Saudi for the first time, back in 2016, His Royal Highness Prince Mohammed bin Salman released a vision called Vision 2030. That vision is a comprehensive plan, development plan for the country towards a vision he has in his mind for this country, and based on the confidence of the government and the potential of its people. This vision is based on 3 pillars: having ambition nation, thriving economy, and vibrant society. And then this vision cascaded into multiple objectives, and there have been more than 10 programs to realize that vision. All of these put together to have, a vision about Saudi Arabia and diversifying the economy, having a vibrant society, having people fit, doing more sport, being advanced in technology, and many things. It's very interesting if you never have heard of it, to read about it. Just go to Vision 2030, you will find everything in the website. So, and Vision 2030 has it's not just a plan, it's actually a very bold ambition about transforming Saudi Arabia into a digital economy. Starting from, if you live in Saudi Arabia, starting from, digitalizing some services like ABSHIR, like everything we can do today in ABSHIR. Last month, I renewed my daughter's passport. I actually didn't do anything outside of the house. I took my phone, opened the ABSHIR, took a picture for her in the phone, uploaded the picture, requested a new renewal for the passport, and the passport was delivered to my doorstep 3 days later. nothing. Like it's all automatic. I even didn't go to, to take a photo for her outside of the house. That's one is Abshire. The other thing is like Neom. If you heard about Neom, it's the first cognitive city in the world operated and managed by AI. Of course, this is still work in progress, but there are a very big achievement in that. So all of that is actually aiming to become towards the digital economy. A lot of the vision objectives are related to the digital economy, from privatization to supporting innovation to economic diversification, improving services quality. And those are some examples that I just mentioned to bring those objectives to reality. If we take a look about the digital economy in Saudi Arabia, it is expected to grow significantly to 82 billion by 2029, with more than 10% growth rate yearly. And the key digital economic drivers in Saudi Arabia are basically around public cloud, artificial intelligence, and Internet of Things, with $5.2 billion expected for market size to 2029, 7.2 billion market size for AI by 29, and 11.5 billion Internet of Things market size by 29. All of these make sense in engineering setting, like we are a KFUBM, all of it related to what we do in this area of the world, KFUBM and Aramco, and in the gas sector. Why AI? Well, because we live today in a world increasingly shaped by AI. Starting from economic value, AI is believed to bring more than 7 trillion or 7% for the next 10 years for the global GDP. AI will increase the productivity of the people, how they perform work, by 40%. AI, it's not just, until last year, like 2 months ago, the biggest investor in AI was private sector, led with the giant tech companies like Microsoft, Google, Salesforce, you name it. But just 2 weeks ago, if you haven't heard about the Stargate, US government announced $500 billion investment in AI, especially in the infrastructure for the next 5 years. Only for the next 5 years. Unheard of. This number is unheard of before, Closely before that, Saudi Arabia announced more than $100 billion also investment in AI and infrastructure. Next week is LEAP, and a lot of announcement will come also about the investment in LEAP in Saudi Arabia. Microsoft, back in 2019, I swear, I was in Microsoft. I was an employee at Microsoft headquarters in Redmond. When Satya Nadella invested $1 billion in OpenAI, we didn't believe in it. We were like, why he's investing in OpenAI while we just give us a bonus, instead of spending all of that money on non-profit organization. We didn't believe on it. He kept asking us in every meeting and every town hall, across the chain, all the leadership chain, until my manager, to put GPT in our products. And today, you see it. Copilot is everywhere. It's changing. It's a game changer. It's changing how even we perceive our life, our work, our education for our kids, and so on. So Microsoft invested $1 billion back 2019, followed by $10 billion in 2023. Yes, in 2023. And last 2 months announced $80 billion investment in AI. 3 out of them is invested in India. Some of them will contribute to the cloud they are building in Saudi Arabia coming 2026. Google, Salesforce, you name it. And of course, investors, year-over-year increasement in joint venture and AI. Everybody's investing in AI. With in 2024, it's raised up to 56 billion, with more than 800 deals around the world. And again, why is AI? Because the global, worldwide, there is a recognition for AI, and there is a framework to make it safe and secure. With the release of EU, European Union AI Act, that make a significant milestone and make people more comfortable in investing and going towards the AI. Why AI in Saudi? Because the Saudi Vision 2030, out of the 96 objective of that vision, the direct and indirect objectives, there are 66 direct and indirect objectives related to data and AI. So Saudi Arabia actually aims to, with that vision, moving the nation, having a vibrant society, and trusting the people and the potential. We have a vision in Saudi Arabia to be one of the top 15 nations by 2030 in AI. Not just that, we have a vision about having smart cities everywhere. We have a vision to develop data centers. Yesterday was an AI tour event in Riyadh, and they announced it's going to be in 2026 instead of 2027. Google as well is already cloud in Saudi Arabia. Amazon is also building a cloud in Saudi Arabia. Aramco is building one. Kaus is building one. Sadaya is building one. There is a huge investment in data centers in Saudi Arabia. More than 300 AI and data startup. Also, we want to develop and attract more than 20 data and AI expert specialties here in the kingdom. And we want to triple the digital content market size in gaming, audio, video, and advertising in Saudi Arabia. So we have a big ambition here. It's a huge, and this only started, the vision was started in 2019, and Sadaya was formed in 2019. So now we'll talk about the reality. And when we talk about the reality, it's not just my observation or some media observation no, it's actually based on a UNESCO report was released last month. That report is related to readiness assessment methodology for countries to test or measure how much they are ready for AI. And they released the Saudi Arabian report last month. That report highlighted the ecosystem and the landscape we have here in Saudi Arabia. Most of those, ambition goals, one of the authorities have, or the programs that was established in Saudi Arabia to drive the vision was called Sadaya, Saudi Data and AI Authority. And Sadaya has 3 arms: National Information Center, National Data Management Office, and National Center for AI. Along with the Ministry of Communication and Information Technology, a third governmental agency that is working towards achieving the vision goal in the digital economy is the Communication, Space and Technology Commission, the Digital Government Authority as well, National Cybersecurity Authority, and the Public Investment Fund. All of them are working hand in hand to bring that vision to reality. The report actually focused on AI achievement in Saudi Arabia based on 5 areas. The first one is legislation and regulation. The second one is society and culture. The third one is research and education. The fourth one is economy. The last one is technological infrastructure. It's very interesting report, 80+ pages. If you have a spare time in the weekend to read it, it will open some eyes. So now I'll deep dive. I'll deep dive onto some of the significant findings in that report. For the legislation and regulation, the report highlighted that Saudi Arabia launched distinctive AI ethics framework, along with generative AI guidelines, along with data and AI occupational framework, AI adoption framework, deepfake guidelines, and AI academic framework. That's all the efforts happened so far in that domain or in that area. For the society and culture, the report highlighted that more than 35% of women participate in technology. I can attest to that. Like when I came back from Microsoft back in 2022 and I joined Sadaya, and in Microsoft, at that year, we reported nearly 20% women contribution, like women employee in Microsoft. When I joined Sadaya, I was director for engineering and development, responsible for all the engineers in the National Center of AI. 50 plus engineers. More than 50% of them were women, AI engineers. Not iOS engineer, or all of them are needed, all of them are important, but I'm talking just about AI engineers here. The Kingdom hosted more than 30 participants from 110 countries in the third edition of the Global AI Summit. Launched training, especially for women in fields related to AI by Sadaya Academy, Tuwaq Academy, Apple, Microsoft, you name it. Have scholarship and established partnership with very prestigious schools worldwide for Saudi talent, and developed advanced large language models using Allam and Sautek to preserve the culture, Arabic language, Islamic values and heritage, and modern technology. And allow me to stop here for a moment because I worked personally in Sadaya and Allam and Sautek. For Allam and Sautek, we trained models from scratch. We collected data from scratch. We actually, and it's based on Arabic. We focused on the Arabic because that's a missing gap in the international technology led by the giant tech companies. We've collected the data, and that was not easy to go and collect the data from everywhere around Saudi Arabia. Having the Arabic data, correct them. You know what will you go through when you want to train a model. Allam is actually a large language model. We trained it from scratch. It's transformer based, of course. We used a lot of GPUs to train Allam, and we have it in 7 billion, 13 billion, and 70 billion. The 7 billion version is available in Watson X and in Microsoft Azure if you want to try it. Sautek is a deep learning to transform it's ASR basically, transform the Arabic dialects, different dialects, not just Saudi, into text, written text. And both of them outperform in Arabic all their peers in published paper. So there are actually some significant work happening there, and the empowerment there is amazing. The support we got there is amazing to get these things out of the door. So and to productize them. So the idea is to productize them. Sautek now is used in multiple government agencies, especially in the Ministry of Justice, Wizard al-Adl, for the courts to transcribe the voice into written text. And Allam, as I told you, it's available in Watson X, IBM Watson X, and Azure, Microsoft Azure services. For research and education, 42 of Saudi universities today offer specialized degree in AI, and more than 30K students graduated since the last 5 years. More than 250K school students and 40K teachers have been trained in AI programs. In Saudi Arabia, there have been organized more than 1,200 training camps and trained more than 1.4 million people, graduated 23K out of them. In the research, maybe that's what most of you are interested in. So the research in AI increased from 4,100 in 2019 into 10,500 in 2023. The patent increased from 39 patents only in 2019 to 195 in 2023. And there are more than 15 research centers dedicated to AI in Saudi Arabia. For the economy, just in 2023, Saudi Arabia invested more than $42 billion for AI innovation. 3.9 billion government investment in AI, technology, digital infrastructure, and tech ecosystem. 160% increase or growth in funding for AI startup in 2023 compared to 1 year earlier. And more than 300 AI companies operating in Saudi Arabia as of international. Here it's international AI companies operating in Saudi Arabia as of 2023. For the technological infrastructure, we have 8 supercomputers, and we have that have been highlighted in the top 500 platform. DEAM is Sedaya Cloud. It's a local cloud platform designed to advance cloud computing capabilities, especially for government entities. Because of the data sovereignty, we need data to not, leave the Saudi Arabia boundaries, and among a lot of others achievements. With Saudi Arabia as a leader, alhamdulillah, the report highlighted also that Saudi Arabia is the first in the region in the Global AI Index, the first globally in the Pillar of Government Strategy for AI, the first globally in the Global Cybersecurity Index, the first globally in Open Government Data Index, second place globally in public awareness about AI, and the third worldwide in AI policy publications. We have 5 smart cities indicated in the report, and we are 4th globally in Online Services Index. So now I'll spare maybe 2 or 3 minutes to talk about the journey from AI, from industry, from ambition to reality. Maybe this is very relating to your, in the scientific community. It's all start about, looking into your organization in the industry, finding the maturity of that organization. Are you a digital-first organization, cloud-first organization, data-first organization, or not? And then think about how can you get it to an AI-first organization. Just imagine, start with a vision and imagination. Just imagine if there is a plant, and that plant has a physical asset, exact copy of a digital asset, a digital twin, and then you have a conversational Gen AI plus agent AI on top of it. And have that, plant, all of them communicate to each other and talking to each other. One day you go and you can actually ask the plant, what's wrong with you? What happened yesterday? Tell me why that fire was established. Tell me why the production was more or less on specific date, on a specific time. This is the vision. When you start about that vision, similar to Saudi vision, then you start putting a plan towards that vision. After having that vision, you need to land into a digital transformation journey based on your the maturity of the organization. And that journey will incorporate a process, defining a process, having people with you from the beginning, looking into the data. Where's the data in your organization? Have them in a one lake, for example. Incorporate the technology, on-prem technology, cloud technology, you name it, AI technology, and then having a governance around it. You start by having a decentralized collection of the ideas, all the ideas that you can, move your organization into an AI-first place, and then prioritize those ideas based on many factors: availability of the data, the need of the data, importance of that idea to the organization, importance of that idea to the success of the organization, and so on, and start with the quick wins. Quick wins maybe are the ones that doesn't need historical data, because most of the time when you need historical data, it's a long story. And then go into a process of phases. Phase 1, the funnel and the scoping we talked about, having a POC, minimum viable product, then pilot, then go to a production, and you iterate over those steps over time. And all of that is governed based on the responsible AI. We want a trustworthy AI. Today, it's not even just enough in the era of AI. It's not enough also only to take care of the privacy and security. We also need to take care of the safety. And by safety, I mean look into the product of the large language models. Is it safe or not? There's something called content moderation, if you heard of it. How organizations put a content moderation around whatever Gen AI solution they are using in order to make sure that those output of those Gen AI models are safe for the employee, safe for the society, and safe for the humanity. With that, I conclude my talk. Thank you so much. And if you have any question, please.
So we'll have time for a few questions, please. Yes, please.
Thank you very much for your presentation. So regarding the implementation plan, these 5 steps or 5 phases that you mentioned, so I can imagine there are also difficulties. It's not that easy to implement all these advanced technologies, link them with what we have as information system in our plant and so on. So how to overcome such difficulties? From your experience, I think, because you worked a lot in this area.
Thank you so much for your questions. This is actually a very core question. And the answer of it is long, but I'll try to give you 2 words. When you are a scientist, I have been a scientist, I was a scientist. I am a scientist, but I was like publishing papers one day and then lived in the journey between having an idea from papers to product. 2 things you need to keep in your mind. If you have your model, you're happy with it, with error rate, with everything. To take it to industry, you need to take care of 2 things. The first thing called latency. You will always hear about something called latency, how fast the response is coming out of your model. And the second is throughput. Throughput is how many requests can your model process, or the system that the model will be implemented in process simultaneously in parallel. Sometimes you call it scalability. You know, when you like OpenAI, how many user is using OpenAI simultaneously? You know, so you need to think about scalability. So these are the 2 words you need to think about if you want to go from a brilliant idea in a paper to a product: throughput and latency.
Any more questions? We can have one more question. Any more questions? No more questions? Okay, thank you, Dr. Manar.
Thank you so much.
طيب السلام عليكم. We will have the second talk. We'll have the second talk by Dr. Hussam Hassanin. Dr. Hussam, he's a professor and director in the School of Computing at Queen's University. Dr. Hussam, he's an IEEE fellow. He leads the research in wireless network, in 5G and 6G, and intelligent edge computing. He, as a director of the Telecommunication Research Lab at Queen's University, he also tackles critical challenges in AI and telecommunications. Dr. Hussam, the floor is yours.
Thank you. So I would like to thank KFUPM and the journal and Dr. Bassam for the invitation. I'm not a deep AI person, and I'm wearing two hats when I speak about AI here. The hat of the head of the School of Computing, where I'm very worried about the future of computing education, and the other is my research on edge computing and distributed intelligence and so on. So first I want to take you through a journey about what we call Computing 3.0, which will have information that you already know, but I'm just putting in perspective so that you would see that. So the first question is, what is computer science? Usually when you ask what is computer science, you hear something like algorithms or computation or processing or high performance and stuff like that. But we find that computer science is everywhere. Computer science is an applied science, is in medical field, is in social sciences and so on. And what we are finding out more and more is that computer science becomes the actual science of and engineering of acceleration. Because we can accelerate things, we can do many, many more things than we could have done before. Actually, the previous talk by Dr. Manal is actually was a very good lead or segue to this, because you see all the things that you can do with the power of acceleration that computer science can do, but then we have the usual foundations of computer science. Whether they are the theoretical foundations, the fact that we are going to have good human-computer interaction, the efficiency and the quality of the programs or the algorithms that are developing, and so on. Then what happened last year was really amazing, is that you know that we don't have a Nobel Prize in computing, right? We have the Turing Award for those in computing, but we don't have a Nobel Prize in computing, right? But who won the Nobel Prize in physics? Those who did work on neural networks, whether they are Jeff Hinton or of course John Hopfield, who actually is one of the or the inventor of neural networks. And then the work of Jeff Hinton at the University of Toronto is of course amazing in that sense, and they won Nobel Prize in physics, and the Nobel Prize in chemistry was won by people who are working for Google, who are actually computer scientists, not chemists. So this gives you an indication of what computer science does, or what the science of acceleration can do. So we know about supercomputing. I'm not going to go through this. But all of this was the lead to what led to the revolution in computer science. We heard about the power of computing and the rise of NVIDIA and all the chipsets that they are developing and where these things are, whether they are in private companies or with the government or the military. So all of them there's a rush to get all of this compute clusters so they can do more and more and more, right? And of course, you all heard about what Elon Musk has done, other than the shenanigans he's doing now with you know who. But before that, when he was has more sanity before. So he actually did what is the XAI, and the XAI was an amazing accomplishment that you could put together 100,000 GPUs. I mean, if you are the richest man in the world, you could afford to get 100,000 GPUs from NVIDIA and actually put them together, a feat that would take 3 years in 122 days. That's what happened. That's amazing. And this is already there. This is the XAI model. Okay, so we have that, and then all of these now are running large language models or foundation models, and this you are going to hear all the time. Okay, let's go back more than 30 years ago, and actually I'm going to talk about Microsoft again. So more than 30 years ago, Bill Gates discovered the internet a bit later than actually we did. And then the thing is, he asked everybody to put the internet in all their products, okay? It's like deja vu, and I could not have said that better. Actually, I mean, it's very good that I'm following you in that sense, because actually if you replace the internet with foundation models, this is the era we are in now, right? So this is exactly what happened, and the same guy, right? But actually he did not know about foundation models and what they can do, except also very late, even after the fact. So this was there, okay, in the early 90s, this was said, but it actually applies right now to foundation models. And the foundation models that the era of foundation models we're in now is going to be like the internet when it appeared. And of course, we know what the internet is now, right? So how will foundation models change a business? And Bill Gates actually did not use these foundation models, ChatGPT, for work, except late, okay? So even Bill Gates only started doing this a year ago or something like that. So if you don't know what to do with foundation models, you are not very far from a person who is actually very smart, okay? We know Bill Gates, right? Okay, so where do we go from here? So, okay, so how did this relate? So let's talk about swimming. In swimming and world records in the Olympics, okay, there are a number of peaks in the number of broken records. And every time there is a technology that was responsible. The first one was in the 60s. Does someone know what happened in the 60s that broken record in swimming took place? Somebody must be old or knowledgeable of this, right? Nobody was born then, right? Even me, but even though I'm probably one of the oldest here, okay. So, does somebody know what happened in the 60s? It's the invention of the goggles. Swimmers use goggles, and because they had goggles, it's a technology, okay, that allowed this to happen. And then there was another peak in the 2000s. Does somebody know what this other peak is? The first is the goggles. What is the other one? You remember? That's right. The suit, the laser racer, right? Another technology is banned now, but another technology caused this peak in records, right? So these technologies are advancements, right? That take place. They are not a leap technology, okay? But sometimes there is a leap, and this leap is like no other, okay? In 1968, for the first time ever, Fosbury jumped the high beam or the high whatever, the high jump, okay, backwards. The first person ever to jump backwards. Everybody, what? Okay, this is what is happening now. What is happening now with ChatGPT and the like, to us, is very similar to the Fosbury jump. We are in disbelief of what is happening around us, right? Okay, so what do we do? What is the claim is we have gone through a number of stages in computer science. So the first stage, where we began to use more automated methods in programming and software engineering, this is equivalent to one technology advance. And the next one, where we have begun to use AI as a driver of some of the algorithms we develop. Okay, this was another one. But then right now, we are going through a different era of software development that is happening and will continue to happen. And I think it's going to be like this. It's like everything would be AI native. We are going to use AI agent for software development, for software engineering, and this becomes different. Are we going to be watching the AI agents develop software? To some extent, maybe yes. Where are people getting their software now, right? So all of this is part of this development of things, right? But the first thing is we need to know how to talk to AI agents. It doesn't make sense to ask for a small, large latte, mocha. Doesn't exist, right? If you ask ChatGPT about this, probably there will be a conversation. ChatGPT will not tell you you are an idiot, but it's going to try to converse with you a little bit, right? So with that, we have to know. So prompting, knowing what to say is very important, right? So it's not going to be just any large language model. It's going to be smart, more advanced large language models are going to develop. And it's not going to be larger and larger. It's going to be smarter language models that are going to prevail. And I'm going to come to that, okay? So who is this guy? Does somebody remember this guy? Kasparov. Remember Kasparov? The last man standing, the last man that computer beat in chess. Afterwards, there was no person better than a computer, right? This was an era that ended the human supremacy on chess, right? Okay, so Kasparov lost, and then what happened afterwards? This is the same guy many, many years later. He came and had a chess tournament using computers and foundation models, or the initial versions of foundation models. And here's what he found, and this is a quote. So remember, he is Russian, right? So this is the English that he used. A weak human player plus machine plus a better process, a better foundation model, a better process is better than or superior than a very powerful machine alone. So if you get the most powerful machine alone, okay, it's not superior. But if you get a very skilled chess player and a powerful machine, but they don't know how to talk or deal with the machine, they are going to lose. And guess what? The ones that won here were actually young people who are computer gurus. They won against the chess gurus in that tournament that he did. So what does this tell us? It tells us that we have to develop efficient, smart foundation models. Okay, then the way we talk to computers have changed over the years, right? So you all most of you, if you recognize this, you are old. If you have used it, you are very old, okay? So if everybody recognizes this, probably not some people at the back. I have actually used this, okay? I have used this in year 1 at university, okay? And then we went into text-based. This was amazing. Ooh, I can type. And then what? We went into graphical user interface. And then we went into what? Conversational. This is the stage we are in now. And the next stage is going to be the mind. The computer is going to read your mind, and we are in trouble. Okay? This is the next stage that people are aiming at, right? So we are here now. This is what conversational AI is doing with us now in all these foundation models. Okay, so prompt engineering is very important. Teaching people how to prompt, how to find the answers they are looking for is very important. So actually, this is not trivial. Asking the right questions is not trivial. People say, oh, I don't get the answers I want from ChatGPT and so on, because they don't know how to talk to ChatGPT. If you know what to do, how to ask, how to go from one step to the other, then it's going to be much better. Okay, what is this? This tells you about what is the hype, the cycle hype. This is old in 2023. I don't have the 2024 yet, but among this is AI augmented software engineering. This is something that is among I guess the expectation hypes and so on. Right now, what we do is, this is AI augmented software engineering, where this is what students do now, right? They ask AI for a piece of code. They take it, put it in their larger code, and compile. And if it doesn't work, they ask for another piece of code, they put it and they compile, and they keep going like this. So because the code can be complex, okay, we are limited by our abilities. Remember that chess player who could not beat computer anymore? We are limited in our abilities to do things, right? So what is going to happen? So right now we are writing code with the help of AI, but what is going to happen is, what if the search space for solutions for code becomes bigger because AI is doing the search? We tell AI what we want, and then AI is going to do the search and find solutions outside our limited search that we did earlier, okay? And then AI, the code that's being generated is going to be sent to an agent, and the agent, not you, the agent is going to put it together, compile, and then do the iterative process on your behalf. And of course, the result is humans don't do much in software development anymore, but they have to know how to develop the AI agents. So AI agents are going to dominate. And the thing is, there are going to be billions and trillions of AI agents everywhere very soon. That's the thing that's going to happen. Okay. So this is an example of a difference of the use of AI can do. So if you know about this windshield wiper, right? And it has sensors. And because of the sensors, it knows what to do, okay? What if we have a change in mentality? What if we don't use sensors? We use an image. And through the image, we would know whether there is rain or not. And if we don't perform well, we take more pictures. We have more data. We take more pictures, we do the training, and we are doing better, right? So instead of going and debugging our program and doing more work, we are going to add some stuff to the data set. So this is where the AI and software development become different. It does things that are not typically we have done in the past, right? Okay, so let's go back. How is this enabled? It is enabled through this high-performance computing. And what I want to show you here is that the demand is higher, okay? Demand is higher, what? Because Saudi is spending $100 billion, Emirates is spending $100 billion, everybody wants to get these chipsets and so on, and there's not enough of them. They cannot make enough to satisfy the needs of everybody, right? And also, they have a monopoly on things. This is where I had the original, like this is where we can do different things, right? So I want to remind you again of the beginning of computers. At the beginning of computers, we had mainframes. Some people remember mainframes. And then when we got advanced, we had many computers and PCs, and we were using it, they were personal. And then we had individualized machines, phones, wearables, and so on. So there was a move in this, right? So foundation models right now run on the equivalent of mainframes. We want to bring them to run on cheaper, more ubiquitous machines, and even on our own devices that we have everywhere. Every device everywhere, right? So if we have a distributed AI, what we can have is, we will unlock lots of potential that we don't have right now. One more thing I want to mention is that the Emirates was forced to send Huawei back if they want the H100s and the H800s. You can't deal with Huawei if you get H800s or H100s. And that then becomes politics. How to get over that? So 2 weeks ago, I had the talk up to here, right? Well, it just give me, I started late, right? Okay, yeah. No, okay. Okay, so 2 weeks ago, my talk up to here was almost the same. But then everything afterwards, what changed afterwards? Because life has changed forever, okay? So what happened? DeepSeek. DeepSeek appeared January 20th, okay? We have DeepSeek. The release was on January 26th, okay? Actually, I left Canada on this trip on January 25. I arrived, okay, on January 26th, okay, to whatever. I was in Egypt before I came here. And I arrive, and then hell broke loose. What is happening? Something is happening. It's different, right? The release on the App Store, it becomes the #1, and then the processing requirement of the R1 is much less. The cost to development is much less. And then what? It says that it has a different method of processing. It's, again, the cost is much less, as I said. And then it uses much less resources. And I'm going to come to the resources later. And the performance is equivalent to ChatGPT and the like. That has lots and lots of spending that took place. Then what? Markets tumble. $600 billion of NVIDIA, $1 trillion wiped from the market. This is just in the first couple of days. And then Sputnik moment. How many people remember Sputnik? Sputnik is the Russian satellite that was launched in the early 60s. And this is the US, a second time around, the US was hit by a Sputnik moment, to the fact that Trump said it's a wake-up call and China is slapping us on the face. That's what Trump said. And they had a meeting with the NVIDIA CEOs and so on just about that. So things has become moving very fast. So what else? My claim now is we are on the verge of democratizing AI. AI is going to be democratized, meaning that we can democratize AI if we have the proper algorithmic innovation, if we are free from the supremacy of NVIDIA, if we have open source, and that's what DeepSeek is, and if we have unbiased data, unbiased use of AI models. So very quickly, the algorithmic innovation in DeepSeek is that it uses what's known as the mixture of model architecture. Each is trained on a smaller set, and then The other innovation is that DeepSeek thinks before it speaks, and that's normal for humans. And also, it keeps you busy when it's late, when it shows you how it thinks. The other thing is you can have model distillations, and as again, the previous talk, LLM is a model distillation that you can have, and DeepSeek allows you to have easier model distillations. And the next one is the hardware, and what I'm going to go quickly here is that you can have specialized hardware, and you can have you can even run these. You can even run DeepSeek on Mac Pros, or and the thing is, having open source and being decentralized is going to change the future of AI. And open source is the next one because it allows you to run on your own machine. So you could have a DeepSeek model running on your own machine. You can download it through Olama, and then here you go. You have a foundation model sitting on your machine, right? Where else can you get this? And you can then tweak with it. And there are thousands of distillations already. This is a couple of days ago, and actually I was updating the data up to last night because things keep changing. So every day keep things changing and so on. And Microsoft has it, Perplexity, Amazon, all of them have that. And the final one is the unbiased, and the unbiased actually comes in data, and now we have sources of data that are open for us to use and so on. The unbiased also comes on our ability to tweak the models, including the weights that we use here and there. And finally, we can have our local and private data as well, our own data, trained on our own principles and culture, which was not there before, where we are going to have control and sovereignty over the data that we own, right? And finally, I just want to go back, is that the democratizing AI is just going to change the future once and for all, and we don't need to be at the mercy of the monopoly of open AI or NVIDIA or the like, or Google or the like. This can be developed. This can be done anywhere. This can be done here. And it's affordable, and it can provide sovereignty, and the bias will be gone, and we can have our local models. And finally, I have to have the pitch about extreme edge computing. Actually, my research is about extreme edge computing and edge intelligence and so on. And the belief is extreme edge computing is going to change the way we do things in AI and foundation models and so on. Thank you.
Thank you, Dr. Hussam. We have time for a few questions. Dr. Ayman, please.
Thanks, Dr. Hussam, for interesting and enjoyable talk. I'd like to ask you, computing 3, since you mentioned, what is going to be the impact on computing education? How should we change the education system to take into account all this?
So this is a very big topic. As I mentioned, maybe to a few other colleagues here, as the head of the department, I'm having a full-day retreat. Just the week I go back with the faculty members just to talk about this, because I fear for the way we teach computing is not sustainable. And my opinion is that there are lots of things that need to be taught, including code understanding and code debugging and so on that need to be taught, because most of the code or the snippets of code that are going to be generated are going to be machine generated, AI generated. So students have to understand how to deal with this, how to put it together, and how to debug programs afterwards and so on. Students also have to understand how to deal with agents, AI agents. It is not going to be far-fetched that every student is going to have their own AI agent that they walk with all the time, right? And then there's going to be their agent that is going to help them do lots of things. But why students? Everybody can do that. And we are entering into territory that is not, we don't know, because things move so fast. Like I did not expect that I'll be talking about this, right? So things move that fast, right? So it's amazing. The other thing is we have to worry not only about computing education, but the viability or the need for certain jobs. So certain jobs are at risk. So we also have to worry about that, and certain other jobs are going to be needed. The most important thing that is going to be needed is that people become experts in what they do. If you are an expert in what you do, probably you are going to survive. And I say probably, because I don't know what the capabilities of AI in a couple of years.
Thank you, Dr. Hussam. We can have one more question, short question. Quick.
Thank you, Dr. Hussam. Actually, I have an observation. Maybe I don't know if you have thought about this or not. But it seems all our prediction or all we try to develop or think about is more of a temporary or interim solutions, I call it. Like, I'm glad you started by talking about computing. Even the way we do computing, originally, the von Neumann machine or whatever, it was created based on the idea that a human is coming up with the solution, coming up with a recipe. A program is just a recipe for a machine to execute my instructions or my commands. But is that going to remain the case even in the near future? When we say near future nowadays, as you mentioned, it might not be 2 years, it might be 2 weeks, 2 months, we don't even know that. So what are your thoughts about future of computing?
So the first thing I want to mention is that you're absolutely right, is that our predictions are based on our best understanding of the current, the past, the current, and our best prediction of what is going to happen, and we are limited in that. But there are some people who are actually much smarter than me who can make predictions. So, for instance, the fact that we have phones that we can actually have video calls on was predicted in the 60s. Somebody very smart came up with this prediction that we are going to have this, it's going to happen, and so on. If you tell somebody in the 60s, where we still have the rotary phones, right? Okay? And I'm going to say how many people use rotary phones, right? So if you tell somebody who was at the rotary phone era that he predicted that we are going to have phones that we have video calls on, this is amazing, right? So there are some people probably who are going to be smart enough to have better predictions. And also we may face a situation where what we predicted is not the case, and we have to adjust our path. So let's call this reinforcement learning, maybe.
Okay. Thank you, Dr. Hussam. Now we will have our third and last talk for this session by Dr. Herbert Song. Dr. Song, he is the director of Song Labs in University of Maryland. He is a IEEE fellow and a Web of Science highly cited researcher. His work mainly focuses on AI, machine learning, cybersecurity, and cyber physical systems. Dr. Song, please.
Good morning, everyone. It's my honor to speak at the AJSE Symposium. So today I will talk about neurosymbolic AI, the third wheel of AI. So firstly, I will give a short introduction to myself and my team. After that, I give the background. So next, I will talk about neurosymbolic AI, why, and past, present, and future. Next, I will talk about we are on the way to neurosymbolic AI. In the end, I will give a summary. So in fact, I have been working on big data analytics and the integration of AI with the Internet of Things. So also I give the speeches across the globe. So also I'm the actually impact creator. Thank you. In fact, probably you noticed that my lab is named after my last name. In fact, I'm not lazy. So each letter in the name of my lab represents something. So here, S means security. We conduct research on cybersecurity. Basically, we are very interested in detecting something like the threat, intrusion, anomaly, vulnerability, such like that. Here, O means the optimization. So we care about different optimization objectives like security, safety, autonomy, speed, accuracy, reliability, such like that. We leverage different optimization techniques. So here, AI is the main tool to achieve the optimization. A and G basically various applications like Internet of Things, autonomous and cyber-physical systems, healthcare, such like that. So here, for my lab, we want to answer two fundamental questions. One fundamental question is for the basic research. The other fundamental question is for the applied research. For the basic research, we want to answer the question like this. How can we design, build, and verify safe, secure, and trustworthy AI systems? So for the applied research, we want to answer the question like this. How can we develop AI strategies and technologies to detect events as quickly as possible after they occur? So currently, we focus on two areas. The first one is AI system design and verification. The second one is AI-enabled quickest event detection. For the AI systems design and verification, here, our current focus is neurosymbolic AI. We develop algorithms and architecture. Also, we develop testing and evaluation frameworks. For the AI-enabled quickest event detection, I care about the different applications. I just mentioned healthcare, autonomous and cyber-physical systems, finance, cybersecurity, such like that. Here, what to detect? It's very broad. So here, threat, intrusion, vulnerability, malware, anomaly, such like that. How to detect? Here, it also is very broad. In addition to detect, sometimes we want to know the identity of these events. We call identify. Sometimes we need to know the properties of these events. We call characterize. Sometimes before we take action, we need to know the precise location of these events. It's called localize. So this is the basic information about my lab. So now I will give the background to the neurosymbolic AI, why I started neurosymbolic AI research. So in fact, this is my journey. Originally, I'm the IoT guy. I conduct research on Internet of Things. I developed a counter unmanned aircraft system. So this work has been cited by the US Department of Defense as the #1 reference. Later, I shifted to the explainable AI and transfer learning and incremental learning. So here, so far, our work on transfer learning has been the most cited paper in the history of HLE transactions on AI. Now, I'm working on the neurosymbolic AI. So far, the first 3 papers on neurosymbolic AI in the HLE transactions on AI are from my lab. So I will start with my journey here. So in fact, 5 years ago, in 2019, in the summer, I was in the big trouble. HLE reported me as a hacker. I'm that bad guy. So new technology hijacks intrusive zones. So a professor from Amarillo Aeronautical University has developed a system for overtaking unauthorized and suspicious zones. So this made me in big trouble since, HLE has almost, the 500,000 members in the world. So why I started such the research made me in big trouble. So in fact, the motivation is very simple. At that time, I saw more and more UAS sightings. UAS, the full name is unmanned aircraft system, or just a UAV, or just simply drones. As you know, we couldn't fly drones, near the airport or in and around the, stadium. There is a high risk of collision, also many people on the ground, right? So here, there is a need to develop a system to counter unmanned aircraft system. Such a system should be able to lawfully and safely disrupting or seizing control of the zone. So many research groups and companies, they are working on counter unmanned aircraft systems. So here, I developed a very unique technique because many technologies, they just want to shoot down the drone after they detect the drone. For my technology, I don't need to destroy the drone. I don't need to cause the drone to crash. So this is a unique case. So for the detection part, in fact, it's very simple. I just leverage the concept of Internet of Things. I deployed microphone arrays. So I call Internet acoustic things to detect, identify, and localize the drone. But for the response subsystem, it's very different. So I'm a hacker. I worked on the cybersecurity. So here, I use software-defined radio to decode the radio channel, the frequency the drone is using, the modulation mode the drone is using, and the protocol the drone is using. After I get the decoded information, I could generate fake control command. I send the fake control command to the drone. The drone is stupid. The drone just follow my fake control command to fly away. So I don't need to destroy them. I don't need to shoot down. So here, in addition to the simulation studies, also I conducted the field test in the Daytona Beach Radio Control Association. So the results pretty good. So my research, so in addition to the HLE reported me as a hacker, more than 100 news media outlets reported me as a hacker. So this changed my life. So also, my research attracted interest from government, like United Nations. There is an agency called ICAO, International Civil Aviation Organization, U.S. Federal Aviation Administration. Also, military, U.S. Special Operations Command hired me as a subject matter expert. They paid me very well. Also, other agencies within the U.S. federal government. Also, industry, big and small companies like Boeing, they are interested in my technology. So also we received the award from the HLE, so this is a big award for me. So also, US DoD and the US Army, they found my research very interesting. So in their funding solicitations, they cited my paper as the #1 reference. So you can imagine if your paper is cited by the, the funding solicitation, how many companies will approach you for collaboration. I'm very busy at that time. So one big award is like this. It's a $150 million from NASA. So in fact, here you can notice, the only 5 universities participating in this award. So 2 awards, 2 universities are affiliated with me. One is my former university, the other is my current one. So here, at that time, my research group was not so big like now. So I had to think about how to collaborate with the government, with military, with industry. So after talking with them, I found, in fact, they are very interested in one grand challenge. It's a real-time machine learning for quickest event detection. Different government agencies, different military units, and the industry companies, they are interested in the different events. So like anomaly threat, vulnerability, or electronic communication signals, such like that. So I set up my long-term goal. We want to establish a domain-agnostic, machine learning-enabled event detection framework. So after further discussion with government, military, and industry, they proposed several technical challenges for me to address. The first one is robustness. If we want you to detect something, we care about the detection performance. In terms of detection accuracy, the other is detection latency. The second challenge is explainable, how to explain why your system works well, why other systems don't work well. The third challenge is people are greedy. If we don't have big data, we still like good performance. How can you achieve the good performance if we don't have big data? So I decided to address these challenges, technical challenges. For the first one, robustness, I decided to focus on accurate detection and the quickest event detection, mainly incremental learning. For the explainability, I decided to start with mathematics. So if we start with mathematics, probably later we could explain why, right? So the third one, generalizability. So if you don't have big data, I decided to work on data efficient machine learning. So I focus on transfer learning. So this is, my next work. The first one, XAI. So someone has, mentioned this. So in fact, now, currently, the deep learning is just like a black box. But this is not enough. Tomorrow, we hope we could explain why not, when you can succeed, when you will fail, when to trust you, when you make the mistake. So here, I just, mention, our work. I don't give the technical details. So my lab opened the deep, the black box a little bit. We proposed zero bias dense layer. So far, it has been cited more than 300 times. So here, for the transfer learning, we basically work on the distant domain transfer learning and the cross-modality transfer learning. For the distant domain transfer learning, it means, for 2 tasks and 2 domains, probably seemingly unrelated. But in fact, we could identify the low-level features to link them. So for the cross-modality transfer learning, text is one modality. Image is another modality. Probably we could leverage one modality for another modality. Here, probably if you work on the transfer learning, you should know this paper. This paper has been cited by almost 26,000 times. The second author is Professor Qiang Yang. But after 2010, what happened to the field of transfer learning? Nobody knows. So I assigned my PhD student to work on this. So far, our work has been the most cited paper in AJSE transactions on AI. So here, for the principal keynote today, Garson mentioned, catastrophic forgetting. In fact, our group made a breakthrough for catastrophic forgetting. So our breakthrough is called the rotating memories. So here, in fact, the catastrophic forgetting, it means, when we learn something new, we forget previously learned information. How to avoid this dilemma? So we found, we created one new word. It's called rotating memory. If we represent old knowledge and the new input 90 degrees separately, so the result, in the end, we could avoid catastrophic forgetting. So we provided the mathematical proof. So at the same time, it's very interesting. One group of neuroscientists from Princeton University, they conducted a mice experiment. They found the same phenomenon. So it's very interesting. In fact, human beings are very smart. It's almost 200 years ago in UK. So people invented cross-writing. In fact, the idea is similar to our rotating memories. At that time, people are poor. If you want to send more message to your friend, very far, how to do it? So you can write line by line and then column by column, 90 degrees separate. In the end, you still can recognize what's in the letter. If you don't believe, you try other degrees, 60 degrees or 75 degrees. It's not easily recognizable. So this is, the rotating memory. Also, I talked about how I invented rotating memories in the CXO Tech magazine. So this is the basic, the background. So now I will move on to the neurosymbolic AI. So here, I just talk about when I conducted my research on the counter-unmanned aircraft systems. I encountered 3 technical challenges. In fact, for the AI, in the history of AI, for the first wave of AI, engineers just create the set of rules to represent knowledge for the very narrow problems. So this is the first wave described. For the second wave, in fact, it's categorized. Statistical learning. We create statistical models to train by using big data. But for the second wave, categorizing, we encountered 3 challenges. The first one is generalization. The second one, explainability. The third one, robustness. You can see exactly the same 3 challenges as I encountered in I developed in my counter-unmanned aircraft system. So now, for the third wave of AI, it's to explain. So this is why I made the natural shift to the neurosymbolic AI. So here, for the third wave of AI, basically, we need to enhance all 4 levels of intelligence: perceive, abstract, learn, and reason. So here, how to achieve this? In fact, since 2022, the neurosymbolic AI has emerged as a transformative approach to the AI. So DARPA started and third neurosymbolic learning and reasoning program. So IBM started the first neurosymbolic AI workshop last year. It's a 4th edition. Also, ACM highlighted neurosymbolic AI on its cover page. Also, NSF promoted the neurosymbolic AI. So here, my recent research on the neurosymbolic AI, including neurosymbolic reinforcement learning, testing and evaluation of neurosymbolic AI systems, also symbolic knowledge distillation of large language models, I don't have time to cover the details. If you are interested, you could refer to our papers. So now I will give you more details about neuro-symbolic AI. Why? So here, in fact, 2002 Nobel laureate in economics, Daniel Kahneman, his popular book is Thinking Fast and Slow. So here, in his theory, he mentioned, we have system 1 and system 2. So the system 1 is intuition and instinct. The system 2 is rational thinking. So here, for the system 1, it's fast. System 2 is slow. So here, let's think about deep learning. Deep learning, it's fast. It's just like system 1. For the here, system 2 is like symbolic reasoning. So here, it seems we could apply the two-system theory to our challenges we encountered in the second wave of AI. So this is why we want to integrate neural network deep learning with symbolic representations. So here, for the symbolic AI, it works well in known environment. For the neural network deep learning, it works well in unknown environment by learning from data experience. So if we integrate these two together, so we could leverage the strengths in neural network and the symbolic representations. So here, symbolic representation is just a low capacity sparse representation. For the neural network, it's a high capacity dense representation, big data, right? So here, past. This is neural network. I believe everyone knows this. We have data, we train, we develop, the neural network. In the end, we achieve objective function. So through the data driven update. So this is deep learning, second wave of AI. We encountered 3 technical problems. So here, what's the current? Current, it's like this. Current, we are working on the neuro-symbolic AI. We want to integrate neural networks with symbolic representation. What kind of symbolic knowledge we could leverage here? So here, for the prior symbolic knowledge, we have 5 types of symbolic knowledge we could leverage it. The first one is equations. In mathematics, in physics, we have a lot of equations. So I believe everyone knows, in 2024, the deep learning, in fact, it's AI. AI won 2 Nobel Prizes. For the Nobel Prize in chemistry, it's for the AI use application in protein structure prediction. In fact, it's equation, physics, the first prior symbolic knowledge. So this prize is a success of neuro-symbolic AI. The second symbolic knowledge is a finite state machine. Also, we could, third one is logic in computer science. We could leverage, logical constraints. Also, we could leverage graph theory. Also, we could leverage visualization concepts. Okay. So here, currently, how to integrate neural network with symbolic representation. In fact, now Henry Katz proposed 8+ pathways. So if you want to try, you could think about this. So here, in the future, we hope with the neuro-symbolic AI, we could achieve artificial general intelligence. In the future, artificial general intelligence, AGI, should address grounding, instructability, and alignment. Neuro-symbolic AI has the potential to address all these 3 challenges here. So here, in fact, in a recent interview, I just mentioned, Neuro-symbolic AI, it's a pathway towards AGI. So it's interviewed by solutions review. So here in the future, probably by integrating neural representation with symbolic representation, we could avoid the first Tesla accident in the history. So it occurred 7 years ago. So here, on the way to the neural symbolic AI, currently, from my perspective, the emerging neural symbolic AI topics include the optimization, representation, also reinforcement learning, scene perception and understanding, also transfer learning. So here, I shared my perspectives on neural symbolic AI with different media outlets like HLE transmitter, how to get AI right, 3 challenges for the future, also inside big data, also the CX Tech magazine again, also solutions review. So also HLE, this year, just the HLE org X account, also neural symbolic AI for cybersecurity. So now, in fact, if you are interested in neural symbolic AI, we have a book coming out. It's neural symbolic AI. We cover the foundations and applications. So it will be published this year. So also we covered several different applications if you are interested in application. So now I conclude my talk today. So if you have any question, so I'm glad to answer it. So here is our reference. It's our recent media coverage. Thank you.
Thank you, Dr. Song. We have 5 minutes for QA. I know it's before lunch, but yes, please.
Thank you. This is Fale. I'm sorry about my voice today. I'm from healthcare side. I'm a clinician and scientist in biotechnology innovations. I enjoyed part of your presentation. I'm sorry because I came late a little bit. But how do you see the digital twins or digital biotwins? Now, mental health is one of the big challenges. And AI-based solutions is very promising, regardless the restrictions and regulations that's going through now. How do you see the digital biotwins placed now for mental health ongoing challenges like Alzheimer's, brain injuries cases that can replace or maybe activate the damaged neurons, especially we're talking about neurons symbolic. And also questions number 2, just to take, you mentioned the 3 waves now, also personalized medicine, very much relying now on artificial intelligence analysis. How do you categorize and also explain this data, which is huge data with a lot of variables that can give high accuracy? Because at the end of the day, in healthcare, anything touching the human body or the life, it has to be evidence decision made to convince the healthcare professional to make a decision with very high accuracy. So 2 questions. Thank you.
Okay. Thank you for your question. It's very interesting. For your first question, digital twin. So in fact, I think the digital twin is very closely related to the transfer learning I mentioned, because for the digital twin, we need to close the gap between the simulation and the reality, right? So here, how to bridge the gap between the simulation and the reality? I believe we need to integrate symbolic knowledge. In this way, we could bridge the gap between the simulation and the reality. So in fact, this is one of my current project because in fact for the digital twin, in fact you think about this. Another opposite question. It's like this question is in fact from my collaborator in DARPA. They care about before we start some the action, the main thing we need to simulate, right? Typically, we need to do a lot of simulation, but now, the simulation takes time. So we don't have enough time. So someone told me, if we start one mission, probably it needs, 1 month, the simulation time. But typically, we just want to start this mission, in, 24 hours. So how to bridge this? So our idea is to, leverage symbolic knowledge in this gap. We want to make sure, the simulation closer to the, real environment as close as possible. The second question, also for you, you mentioned, for the healthcare, you want to use this. I believe, here I mentioned, if we want to leverage neurosymbolic AI in healthcare application, we should use, the prior symbolic knowledge. I believe, here, I mentioned five, the knowledge. I think, probably equation, doesn't work for this. But from my experience, it seems I did some work on health. I used some, the symbolic knowledge like finite state machine and the logic. It worked well. I think probably you could try, these two first. And then if these two work well, it's fine. If it doesn't work, probably you could try, the visualization and the concept. Let's see, if this can generate, the result you desire. Thank you.
Thank you. We can have one more question. Yes, please.
Thank you very much for your presentation. I think it's very interesting. I definitely look forward for your book. I have actually two questions. The first question is about, this neuro-symbolic AI is becoming popular recently. So logic-wise, it's quite natural, right? So when we consider how machine could, consider things like a human, a neural network and symbolic reasoning, they are quite natural. What make this popular recently? And also from now on until, you see some significant application, what are the major barriers?
Okay.
Thank you.
Okay. So in fact, for the first question, it's very interesting. Basically, it's for the three challenges. The explainability, generalization, also and the robustness. Deep learning, the second wave of AI, they couldn't address these three challenges. So we had to think about out of the box. Probably we combine different approaches, we could, address these challenges. So we still use deep learning, but it's not enough. We just integrate deep learning with symbolic representation. We hope we could address these three technical challenges. In fact, for your second question, this one is very interesting. So here, for the neurosymbolic AI, so in fact, for the symbolic part, it's not new, right? Symbolic AI already there for, the several decades. For the deep learning, it has been worked, for many years. But the problem is how to integrate. In the end, I mentioned, the Henry Katz. That guy, in fact, he was the division director of IIS within the size of NSF. So he mentioned, he summarized 8+ pathways to integrate neural networks with symbolic representation. But which one will be the dominant? Nobody knows. He still summarized, the new, the advances to fit his pathway. Probably, this is the biggest obstacle. We don't have, the framework. We don't know which integration approach is the best. We're still working on this. probably it takes, several years to figure out, the dominant integration approach. After that, we could, apply this framework to the different applications beyond the autonomous driving, beyond, probably, autonomous driving is related to your, field. Transportation, definitely, this is the first field. So I believe, the integration, how to integrate, is the biggest obstacle. Thank you.
Thank you, Dr. Song. By this, we come to, thank you, Dr. Song.
Yeah, thank you.
Thank you. By this, we come to the end of this session. We will take a break till 1 o'clock, inshallah. We'll have lunch, prayer and lunch break now. We'll come back at 1. See you all at 1. Yeah, lunch will be served, please. So lunch for everyone, please. But after prayer, inshallah.
Okay, Bismillah ar-Rahman ar-Rahim. I would like to welcome you to our next session. Our next session is titled AI and Digital Twins as Enablers of Future Power Systems. And we have actually power systems reinvented with AI. So our next talk is AI and Digital Twins as Enablers of Future Power Systems with our distinguished speaker, Dr. Georgios Konstantinou. Dr. Georgios is an associate professor at UNSW Sydney. He's leading the real-time simulation lab, and his research integrates digital twins, power electronics, and AI for future power systems. Join me in welcoming Georgios.
All right. Thank you. It is indeed very bright up here. Usually we fight to not have the session after lunch, even when we are teaching back at the uni, because just after lunch it's the hardest time to keep everyone going. But I'm here to talk a bit about the work that we are doing in implementing AI on energy systems, well, power systems to be specific, and power electronics. And where do we see the value of this work? So the idea for me is not to cover anything that relates to development of AI. This is certainly not our expertise. You're not going to see any new developments on AI from my presentation. It's more of a, how do we take the AI tools or the different tools that are being developed by people in computer science, a lot of you here in this crowd or outside, and implement them for certain applications for power systems. I do have to mention that a lot of the work that I'm presenting here, I do have to acknowledge the work that my research group, my students have been doing in this area. And you will see that coming out of the later presentations, we're presenting the work that we have. Now, a bit of motivation, so I can give a background on power engineering, and why we're working in these areas at UNSW, and what are some of the unique issues we have in Australia. Some of them are common around the world, some are very unique to what we have to deal down under. So one of the challenges that we have that is very specific to Australia is the uniqueness of the Australian power system. So even if any of the solutions that you would see developing in power system are directly applied into or can be applied in different power systems, the type of network that we have in Australia, and by type of network I mean it's an extremely long network, but it's a very weak network. We have generation being located very far away from the load centers, and now with more and more renewables in our system, it's becoming more and more difficult in terms of integration, but also in locations around the Australian network where we put our solar farms and our wind farms. And also the network itself. So if we look at the mesh structure that we have as an Australian network, it's very, very different to most of the networks that exist around the world. So we can see that direct solutions from everything that is being learned around the world is not applied in Australia. We have to do our own things down there. Now we have some things that relate to unique power system challenges in the modern environment, and that has to do with the timescales, because delays in some of the other processing, or how long it takes for ChatGPT to send you an answer, is not as critical. It can take 1 second, 2 seconds while it's thinking. But power system is a live environment, a real environment, it's a fast environment relatively. So we have to make decisions in milliseconds in order to maintain its operation. And with more and more power electronics, which is the difficult thing for us now with integration, we are moving down and down the scale into smaller and smaller time steps, which makes the overall analysis and the tools we require in order to understand the system a lot more complicated. And finally, the importance of the detailed large models for power electronics defined grids. How do we better replicate and represent what is being installed in our systems, in our models, in our network? How can we learn what is happening in our networks, and how the tools that we have been using for what is now 20, 30 years, what you see there as the red line with the RMS results, is no longer sufficient to capture the dynamics and to capture the oscillations and to capture a lot of the issues that we have in our system. So we come with this combination of problems, and we identify that we need to have targeted research and development for what we have in our network, robust platforms, and also these realistic and more representative networks of a modern power system. So in terms of the work that we do, not related to AI in general, in our lab, we have these three main research areas. We're talking about power electronics dominated power systems, so this transformation from a system with synchronous generators to a power electronics system with wind, solar, batteries, and anything else that connects with a power electronics converter. Medium voltage DC systems as an alternative solution to our AC system, especially for integration of renewables, and power system digital twins, which I will touch a bit later in our presentation. Now, we are the real-time simulation lab, but this is actually a combined lab. We do have our main real-time simulation lab, so pure computing, but integrated to that is a power electronics laboratory. So we are able to do a lot of actual tests in actual equipment, well, scaled down laboratory equipment, of course, not the big system, but this allows us to put together a rather complicated map of equipment, hardware, and external device that we can connect in our lab in order to do a lot of these tests. Now, we do a lot of these things because we do want to have not just the research, but also the impact in what is happening in Australia and then around the world. Some examples of practical issues that we had to address comes into, again, back to the uniqueness of the Australian system. One example is integrating energy storage systems. This is an example of a battery that is placed in a location that could resemble some of the deserts outside here in Saudi. It's a very remote location. It's also a desert location. It's electrically a very weak location in the network. So better understanding how we can optimize these systems and how we can make sure that in an area that we used to have synchronous generation and now we have power electronics with solar, wind, and batteries can maintain its stability has become quite critical for us. Some other work, integration, hardware in the loop testing for our small scale inverters. We have been running a project trying to understand and how eventually how we model the representation of large scale DER in Australia. Probably you're not aware of that, but Australia it may not be leading in terms of renewable energy penetration, but is leading the world in terms of small scale renewable penetration. So the amount of 5 to 10 kilowatt small scale systems in the roofs of houses. In terms of that, Australia is actually leading the world, which creates its own, again, unique environment. Again, how does it take us to understanding the networks better? So far, nothing I presented here directly relates to AI, but sets this stage on which we will try to explain where we are coming from with the applications of AI in order to address some of these problems that I mentioned here. Now, preparing for this presentation, I had a look on when we are talking with my students and in our group, when we are talking about AI, what comes in mind? Again, we are not the AI experts here. We are the ones that take the AI tools and try to make use of them in a power system. So we looked at some of the easy ones, machine learning, computer vision, expert systems. What can we do with optimization and search, agent-based systems, and so on? And we realized that in a lot of these areas, there are experts that and already existing applications for which the power engineer being the one that takes the lead in the application of AI does not necessarily make sense. So some examples here, we have computer vision that was covered very well earlier in the keynotes, where tools are being used now to understand the condition of parts of the network. So we use drones in order to identify faults in transmission lines. Again, this comes back to computer vision, not necessarily the expertise area of a power engineer. Large or natural language processing, how can that be used in the control room of the future? Again, a lot of work being developed there, but the power engineer is not going to be the expert on large language models and this communication. And other examples here. So we had a look at what is the tools that directly come from the suite of tools that I mentioned earlier, but make a lot more sense to be used in the less attractive areas of power engineering and what problems we can solve with them. A few of them go back to traditional machine learning. So we're talking about classification, clustering, regression tools. These, again, have been around for a couple of years. So not necessarily the focus of the work we do with my group. where we're actually looking in this left side here, the learning method. So how can we actually make use of deep learning algorithm, reinforcement learning, and some transfer learning in order to improve power system and power electronics integration aspects in our network. Now, all this sounds good, but power systems have been around a lot longer than AI systems and a lot longer than data. All the tools that will be discussed for the next 2 days here have been around. And that creates a very unique set of integrating what is really modern technology with the legacy systems that exist in power systems. So some of the key issues we identify here, I'll start from the middle. First of all is quality of data. We are looking at combinations of where we collect data in a power system that could have very different timescales. We could have slow data, very fast data. We could collect things every 4 seconds, every 1 second, every few milliseconds. So how do we put them together? How we time synchronize them? Because in a power system, everything needs to be time synchronized in order to make proper sense of what's happening in the network. And how do we make sure that even the noise that is being captured doesn't affect the results that we get? Represents a big challenge for operating in power system. I did mention legacy. We do have a lot of different formats, some of them going back to the 70s, some of them to the 90s. Every time we have a new generation of equipment coming into a power system, we create new data or data files and data formats. How do we integrate them? And how do we make sure that we can use this reliably in order to make decisions with AI becomes a problem. Finally, one of the most challenging things, and digital twins become important here later, is data availability, because our goal for the power system is a reliability level of 5, 6, 7 nines. Remember the number, 7 nines. So this means that not much is happening in a power system most of the time. So when we have things happening in the power system, they are very unique. How we capture these events, whether we have a fault in a line, whether we have any kind of event that could be used in order for us to train data, to create data for us to train our models, is quite complex. And even if we have this data, how happy and how confident we are with the labeling of the data, what we have captured, where things are located in the network, all of these things do create a very, very interesting and very unique set of challenges that we need to address in a power system. So why do we even bother? Because we do have our traditional techniques. We don't have to go to AI in order to solve a lot of the problems. But we realize that the complexity of the structure of the power system changes a lot. And in the last decade, the things have accelerated even more. As I mentioned, we do have a lot more renewables coming into the system at large scale, but also at small scale. We anticipate a big growth of electric vehicles, which will also introduce problems because electric vehicles effectively are power electronics components, solar, distributed generation, and so on. So this high proportion of power electronics pretty much covers everything in our network. It does create a problem for which we need new tools to work with. And this introduces also new stability challenges and new interactions in our system. So we now have to start worrying about interactions not only between oscillation modes of synchronous generators, but we have to worry about oscillation modes of a solar farm with a wind farm. How do we make sure that we optimize the operation of a solar farm that is generating nothing in the middle of the night, it's generating at full power in the middle of the day, a power system that continuously changes simply because the way that we generate our power is now a lot more reliant on weather. It's a lot more intermittent, and it's no longer this controlled, constant power out of our thermal power plants. On top of that, we do have to worry with things like cybersecurity, the amount of data, and decentralized ways of capturing data, but again, not our area of expertise. I'm not going to be touching on this. So one of the first applications that we see, that we have developed in terms of power AI introduced into power electronics and power electronics operation takes us to reinforcement learning. So what we have here is a traditional integration of a power electronic system into the grid. So what I have is my power electronics converter. Think of it as your solar farm, think of it as your wind farm that is connecting to a grid. So what we would usually do is we would set the control parameters inside this once, and we would just go away and never look back until something happens to our network. So usually we'd have these farms with the same controllers working for years and years and years. And one of the examples of instabilities that I mentioned earlier, in Australia, we actually had problems because all of a sudden we built more and more solar farms. They started oscillating, and it was eventually the tuning of these controllers internally that was creating all these issues. So the question is, I cannot go back and try to re-optimize or redefine gains for every single solar farm every time I build a new solar farm. How can I do that in a better way? How can I do that in a faster way? How can I do that in a way that kind of validates the stability of the system that I have here? Also, we do have to worry about where our system is stable as the system progresses. So today, I have my synchronous generation. 5 years from now, I will have half of my synchronous generation. 15 years from now, I plan to have none of my thermal plants and my gas-fired power station online. So a plant that was stable today could become unstable in 5 years, could become unstable in 15 years. So what we looked here is effectively a deep reinforcement learning approach where we developed the model of our converters, the model of the plant, and through our own small signal model that we're able to identify from the network that we have here, we're using an actor-critic approach. We're able to train and optimize the gains for different operating conditions. And what this allows us to do is, regardless of where we are in terms of day, year, we have some optimal operating points for which we can tune our converters, and we can tune the controllers of the converters in order to maintain the stability of the operation. So in terms of development and training, we did have the actor network with the critic, a few neural networks here, the activation functions, and so on. What we set as the optimization, or the reward, if you want, so what was the focus of our optimization, was effectively the phase margin of our system. So how do we make sure that we maintain stability under all conditions? How do we make sure that this actually continues operating in a progressive transitioning power system? So we played around with weights. We were identifying which weights would be optimal. We see that the weights, the approach is not really dependent that much on the weights. Some are better, some are worse, but it's not the most critical part of the work here. And eventually we end up with this set of control gains that are defined for different operating points that have been identified through this deep reinforcement learning that allows us to operate our system stably. So what we found here is that with our adaptive control gains that are changing based on the training that we had, we're able to get a very stable system, and we do have very rapid power tracking, something that we could not achieve if we are just using our normal gains, whether they are small or large. So we do have a combination of the benefits that we would normally have from our traditional linear tuning of our controllers implemented through this deep reinforcement learning. Now, we did this for one system, and that's the work that we did in collaboration with our colleagues at Nanyang Technological University in Singapore. We also took the system, validated experimentally. So saying important things in power engineering and power electronics is to actually demonstrate experimentally that this thing works. So we put our converters that we trained the controllers and the gains experimentally. We got the results that we kind of anticipated, and that's always good in terms of these results. We're able to maintain system stability under very weak grid conditions and also implement this satisfactory dynamic performance. Then the next question, this was a work that was actually led by our colleagues in Singapore. We had to see into transfer learning, because you optimize or you develop a controller like that in a solar farm, but you want to see how it would work in a different solar farm somewhere else in the network or in a wind farm and so on. So again, traditional concept of transfer learning, we have the model that we developed, that we trained. How do we retrain it quickly in order to be able to use it in a different location with different characteristics? So we could think about different renewables, whether it's a solar system, whether it's a wind farm, whether it's a battery energy storage system, or in different conditions, whether it's connected near our original location, somewhere remotely, somewhere that we have never connected the renewable energy plant before. So again, as I was saying, same ideas. Train the model as we did before, get the pre-trained model, implement it with a transfer learning into a second target, and make sure that this will continue operating stably. So what we have here is our original system, good dynamic response, a very stable system, controller 1, target 1. We take it as it is and we apply it in our new system and what we expect to have the instabilities that we thought we were going to get. So you see the phase margin here, we are completely unstable. Our system really quickly goes into instability. We implement the transfer learning, and what we have is a completely different system, again, similar controller approach, but a completely different power rating, location in the network, system strength that it connects to, and we get back our good dynamic tracking and our good stability through the use of transfer learning. Again, normal controllers, but optimization and learning of the parameters that we want to implement for given conditions based on learning approaches. The next thing that we saw that's quite useful for the work we do is taking the ideas from convolutional neural networks together with physics information, because again, we're working on a power system, we do have a physical model out of it, and we want to make as much use as we can, simply because we know what is there. It makes no sense to not use the physical information of our network. So we are looking into a medium voltage DC system. We have multiple converters that interact with each other. This could be typical inverters connecting to an AC network, DC-DC converters, all of them different in type, different control strategies, different everything into it. We want to make sure that we can optimize the power flow in this system while meeting all the constraints that we have in our network. And if we try to do that with traditional power flow approaches, we see that we are not very flexible in terms of how large this network can get before we are not able to run our power flows in a computationally efficient manner. So again, taking the conventional convolutional neural network, which I will not spend time because I think you probably know that better than I do, we take input channels, again, physics information to our network. We have voltage, power, current, the different groups that we have implemented in our controller in order to facilitate power sharing, and also the configuration of the network that can change, and it's important in this discussion. And then we combine a few. We try to simplify as much as we can because we're eliminating the additional input channels simplifies the overall network that we built. And we end up with a configuration together with our physics information that accounts for losses, current flows, and voltages in our medium voltage DC that allows us to accelerate the solution of the power flow in our medium voltage DC system, but it also allows us to be a lot more flexible for operating points that we have not seen before, and also for conditions and changes in the network that we do not necessarily train our system for. So different types of systems. We had a simple 4-terminal system all the way to a quite large 10-network system with DC loads, AC loads, batteries, electric vehicles, loads, generation from everywhere we could. And we were able to pretty much define and train these models in order to achieve these goals. So pretty much the process there. And our focus also on this system being resilient enough when we have faults in our system. So we're also very focused on what happens when we have multiple converter disconnections or what happens when we lose transmission lines into our system. So this work, together with our colleagues in Denmark and also Dr. Khalid here in KFUPM, we were able to demonstrate substantial improvement, particularly, again, you can see in the trained area, we expect, regardless of the different networks you are using, to get a good accuracy and not a lot of error in our results. What we do demonstrate here is, though, that an approach that uses the physics information and the training that we presented earlier improves for operating conditions that were not seen by the network before, and more importantly, what happens when we are having a varying network topology. So faults in our system for which we did not necessarily train our models, we're able to get a substantially better and faster power flow calculation and reconfiguration of the network than we did with our normal previous approaches for power flow calculations. And finally, the third part takes us to digital twins. We had a discussion earlier about digital twins for a human. We are looking now in a digital twin for the power system. And the main concern that we would have from our point of view for digital twins goes back to the, if you want, the slow changes that we have in the industry of the power system. So we're not going to just take any AI application and throw it in our power system engineers are a lot more conservative compared to just training a car and letting it loose on the streets and crashing wherever it cannot identify snow or the line in the side of the road. So what we want to demonstrate here is how we can use the AI approaches in order to not only develop the data that we are missing from our power system, again, because we do not have that many non-steady state, everything is working fine data in our network, but how can we also validate the applications, the AI applications that we are developing in a close to real environment. So in this case, we are looking first of all at the tools that we have, and we have real-time simulators in our lab, so we're looking into how do we take the real-time simulations and develop a platform that allows us to exactly define that. So we present in a paper a couple of concepts on how we would do this. How do we have this central database that allows us to optimize or to maintain all the information that we think is critical, and how we can build these loops around it that together with the physical twin and the representation of the virtual twin allows us to effectively achieve all these goals that we have set for our digital twins in a power system application. Now, the first proposal we had here was in terms of the modularity of the digital twin for a power system. Our power systems have quite a lot of applications that we need to build on top. So we want to have digital twins that are modular so that we could put together the functions and allow us for this integration and versatility for our system. And developing the networks that we have here, we're able to pretty much, I'll go straight to the concept of the virtual physical twin, where we are effectively integrating what we have as a digital twin with a representation of the physical twin, all in the same lab, that allows us to iteratively train and demonstrate all the applications that we have in our system. So kind of put them together, put a network model in between, you bring your AI application or any application you have for your power system, and we're able to validate against your claims for not only operation and validity, but also for real-time operation, because there's a lot of work on AI applications for power systems that works well in a very slow simulation, but when you apply it in real time, it actually becomes quite complex to validate. I will close, I'll take 30 seconds more to get to the challenge that we have for our AI systems. It's not a rosy story for power systems because we have a lot of challenges that we need to address. We need to integrate with legacy systems, and that's not going to go away for a lot of years in the future. The complexity of the computation that comes because of how big the systems are, and how do we want to make sure that these exist, and how do we make systems that are scalable to account for the change in the system is really, really things that we need to think about. And then, again, things I mentioned earlier, quality, cybersecurity, robustness, fairness, and how do we make sure that the regulators that we have, especially in Australia, that are quite strict, are satisfied with what we are putting in our system, and that we maintain an economical, reliable, and well, stable system for power. And that's from my side. Thank you.
Thank you, Dr. Joris. We have time for a few questions.
Not clear about the digital twin here. Are you creating a digital twin for part of the network or for the individual, controllers?
So in the last part that I was discussing, we are building a whole network digital twin, but in order for you to do that and to be accurate, you also need to have at least smaller scale modular representation of the different components in the system, which I kind of introduce a complexity. You can have your digital twin of the system that really requires digital twins or smaller digital twins of the components in there. And then you can play with the level of accuracy. But for us, it's not only developing the digital twin, because to develop a digital twin directly of the whole system is extremely complex and very expensive as an exercise. What we're looking here is, how do I have something in the lab that acts as a physical twin and a digital twin that allows me to have a controlled environment for which I can test for the many AI applications that exist around. Like there is a lot of, use this AI to do this in the power system, use this AI to do in this power system. how do we train that? How do we make sure that they actually do what they claim to do? That's our main concern here.
So you practically is focusing on doing that for prototyping and lab validation rather than deploying?
At this stage, yes, because we don't think that you will be deploying things that haven't been validated. Like it's the power system conservatism, if you want. We want to make sure that things will really work before we scale them out.
Okay, thank you.
Thank you, Farhad Diaby. Questions, this following my colleague questions, how do you validate digital twins when it's come to the value data for healthcare? Are you using baseline collected data to simulate and then you can take this as a reference? Because validations, data without validations means nothing.
So the question here is what you're trying to validate. If you want to validate your real system, and that's one of the difficulties that we're trying to kind of bypass with what we're doing here, is if I am building a digital twin of a real part of the network, I do have this extra task of validating that the digital twin I built is actually corresponding to what exists in real life. Whereas here, we are developing the digital twin based on a model that we have already validated against, whether that is a synthetic model, and we do have small or very large synthetic models that we can build against. And that kind of removes exactly your concern. It means that I don't have to go back and validate that the digital twin corresponds to the real system, which is extremely complex and expensive. It needs to validate against my representation of the physical twin, this virtual physical twin that I introduced here. So I have a model that I have validated based on which I built my digital twin with all the uncertainties and things I can introduce in my loop of generating the digital twin. And once I'm confident that what I have is validating against the representation of a physical system that I have in my lab, then I can go and test anything that I have in my system. Otherwise, you have to live with that problem that you mentioned, that I can build a digital twin, but is it really a digital twin of the real system that I have out in the field, which is really, really complex to do.
Which is technically, in healthcare, again, I'm not, because you have to have accuracy to rely on to make it possible to use. Which easier, to collect data, then validate, or validate, pilot, and then collect based on your validation?
Well, in a power system, I think it's slightly different because it's one system. So ideally, you might be able to find all the data. In real life, it's impossible to find all data to be able to build an accurate one-to-one representation of the actual system. But again, for us, our main concern is how do you validate the applications you build on top of a digital twin? So in your case, in your healthcare, you have your human and the virtual human. What we're thinking here is you have a virtual physical human based on which you build your model for your application, and then you can go on top and see, does this application actually do what you want it to do? We think that this is like the important first step to validate any applications, including the AI applications that I had in my slides, before you go and develop the digital twin that you can then roll out the applications in real life. I think that we are 3 steps removed from having real digital twins of the power system that we can use with all the AI applications to give us useful results. We are still quite far away, if you ask me. Thank you.
Okay, our next talk is titled Evolution of the Smart Grid Era, AI-Driven Innovations and Challenges Ahead. And the talk will be given by our distinguished speaker, Professor Haytham Abu Rab. He is a professor at Hamad bin Khalifa University. He is a fellow of the IEEE and co-editor-in-chief of IEEE Transaction on Industrial Electronics. His research includes smart grid, renewable energy systems, with over 600 publications and numerous international awards. Join me in welcoming Dr. Abu Rab.
Assalamu alaikum. And thank you for the introduction. Thank you for the invitation. Dr. Wassam and all the organizers and attendees. So my talk about smart grid actually is so transforming our grid into smart, that is utilizing the AI. Dr. Georges, for sure, he saved lots of my my talk. So let us see. Okay, so I will introduce the topic and then the value of the big data. And we'll talk a little bit about this data and how it can help us, and what are the challenges related to the data from the power grid, some AI-driven innovations, and more intelligence. So this is the traditional grid. All of us know that. So it is unidirectional power flow and communication flow, which relies on the centralized generation and characterized actually with limited interaction. Yeah. Sorry. It's not stable. Limited interaction between the end users and the system operators. Now, actually, the transformation is to renewable energy. So renewable energy worldwide, so whatever we like or we don't like, this is the, maybe I will say here. We like or we don't like, actually, the transformation is to more renewable energies. And just to say that this traditional energy paradigm, the power grid that was established almost 130 years ago, is performing very well in terms of stability, speaking about voltage and frequency stability. However, lots of disadvantages. It was not envisioned to our reality now. The expansion and such long distances with many end users, and many new requirements in terms of those distributed renewable energy generations, and also the electric vehicles and the charging system that are being connected to the grid. So it is a big challenge, moving the functionalities of this bulk power system into the to the grid edge with a huge amount of distributed generations around it. So not only actually that, now the inertia of the whole of the system, the inertia, which is a big advantage of the traditional grid, is now becoming smaller and smaller with renewable energy systems. This inertia is going down, approaching zero. So we don't speak here about only about the fluctuating renewable energies as the challenges, but really the nature of those renewable energy system, I think, is okay. Good. Okay, thank you. Yeah, so it's not only the fluctuation of renewable energies, but the nature, the inertia of the system is being changed, which affecting the whole stability of the grid. So, so speaking about the demand supply balance, is not only here the issue with the voltage and the frequency stability, but everything now is going with very fast response, having lots of power electronics around the grid in terms of generation and in terms of end users. So the generation is reducing from the traditional synchronous generation into more renewable energy that is power electronics based, and the laws are becoming more flexible and more smart. And here we have lots of, let us say, EVs, with a lot of demand on the grid, and the smart appliances also becoming more and more connected to the grid. So speaking here about moving into the smart generation, smart load, and smart utility, smart market. So all this is pushing the grid to have lots of smart, speaking about end users. So here there is no master and slave, but all masters and all active players around this grid. This smart grid, which is called electronet, let us say, or electricity with the brain. So it is a combination or putting together the electricity with communication and information infrastructures together. So speaking here about a huge amount of data being available or collected through this grid, and to manage well this grid, this data should be properly utilized. In the power grid, and Dr. Georgios mentioned about the utility sector, the power sector are conservative in utilizing new innovations, but this is reasonable here. So you speak about the electricity for the humanity. So no one would like to have a lack of electricity. It's our life, actually. So they are very conservative, although now more and more data is being generated and being put around the grid. Some of the data, of course, speaking about offline, that can be utilized and with lots of benefit to the power grid, but in many cases, the decision should be online. And here is the big challenge. So speaking about the big data, all types of the data is available here, and volume, velocity, and variety as part of this power grid that should be utilized. One of the case studies that was done by our students is getting the data, real data, from 105,000 transformers, and this is from the utility in Spain. And the project was funded by a utility from Spain, actually. And the constraints are resources allocation, execution time, and accuracy. So forecasting, load forecasting, 1 day ahead was managed to be done. Shorter than that, of course, we speak about utilizing supercomputers and etc. For the utility, does this make sense? And also exposing their data to the cloud, is it allowed or not? So speaking about lots of challenges for the utility, and many challenges were shown, of course, by Dr. Georgios. And here, the availability, even if the data is available and utilities, they don't want to share the data, not because they don't like new innovations, but it is about the security, the privacy, and the security. They are very conservative, and rarely you find the utility that can share the important data for utilizing certain AI algorithms. And of course, the cost, the execution time, accuracy, scalability, and verifiability that was discussed here. All those are very important. But utilizing this data and AI in the power grid would really move the grid from the old stage of being reactive, and this is the traditional grid, or to the stage of being autonomous. So now we have many of the projects actually from different industries and utilities, including Siemens, Shell, and they are interested in predictive maintenance, on identifying the remaining useful lifetime for different of those important assets, transformers, machines, provide the data. Of course, they are very careful about sharing the data and utilizing the data, but it is of benefit. However, all those are are specific, limited utilization of those data. It's not a wide scale. So our grid is still within this stage and is still far away from being really autonomous. So AI-driven innovations, actually, we saw many of those applications in different areas, including in the grid at different aspects. Machine learning is of high interest in the power grid. One of the most important applications for the AI and power grid is the stability. So stability, I speak about short-term and long-term stabilities. It was reported that 50% of stability failures could be predicted by dynamic data. Currently, most of the studies for the stability is being done, even for the AI, utilizing static data. And with the dynamic here, so you speak about very short period, and you have big power system. So how really you can utilize this machine learning and AI in general for this power grid? There are challenges, but also there are opportunities. So now when you speak about the generation is distributed, and each of those generators, they have their own controllers, and those can be tuned. So this is a case study that is being also done in our team, and this is a project funded by a Scottish utility. So it's about studying the subsynchronous oscillation and utilizing machine learning for the identification of the subsynchronous oscillation, localization, and mitigation. So it's about the type 4 wind generator. It is direct, full, actually, power electronics grid connected generator, the newest generation, the newest solutions for the wind turbines. But because the grid with more and more renewable energy is becoming weaker, so the subsynchronous oscillation is started to appear more and more. And the subsynchronous oscillation actually is caused by extensive transfer of energy between turbine generator at the system natural frequency. So this causes significant instability. And here about training, having a certain machine learning algorithm to identify and to localize. Traditional methods actually require accurate dynamic models, and the scalability is a problem because always you make the model at smaller scale, bus system, and then you need to scale it up. So it is challenging, and utilizing the machine learning could be of high help. And reinforcement learning is because you need a light machine learning model, because finally you need to put things on a controller, and usually those controllers are industrial controllers. So you cannot put a highly computational system on the controller within the power electronic system, the inverter that is being used. So this one, they succeeded to do that in 3 cycles and tune the controllers online. Of course, there are challenges with the data in real life and how to implement with that and how to get the real data. So with such kind of instability thing, how to get real data. So synthetic data actually are the realistic things. However, once tuned, then you can implement on a real system. So more intelligence, speaking here about really those DGs, power electronics converters, because those become major players in our grid in the future grid paradigm. So this is an example of virtual synchronous generator. So now the issue how when we move for more and more renewable energy systems, then we have less synchronous generations. So the whole grid stability is could be jeopardized. Then how we can have our DGs to mimic the behavior of the synchronous generators. So virtual synchronous generator is try now to support the grid, not only in active and reactive power, but starting saying, okay, what about the inertia of the system that's going down? So how we can support that? And also supporting the inertia of the system. Then the system is evolving. So the whole inertia is changing in the power grid. So how this DG can identify, how can be smart enough to identify the needed by the grid level of inertia to be supported. So those DGs are now under very tough requirement to support the grid in different ways. As I mentioned, not only speaking about active, reactive power, but also about the inertia, the behavior, the stability of the system. Training, of course, those DGs is very, very important. Another research that we are doing is building a multi-terminal charging system with renewable energy with PV system and connected to the grid and battery storage as well. So managing such kind of system so that the system can rely as low as possible on the power grid. Charging one EV, the charger, fast charger, can take 500 amps from the grid. And always charging the batteries, you start from constant current mode. So you push the maximum current at the beginning. So this is very, very huge current for charging one EV. So a big train like the one going from Medina to Mecca is around 10 megawatt connected to the medium voltage, draws around 500 amps. And now if you have this connected to the downstream of the grid and taking 500 for charging one car at even a short time, this is a huge challenge for the grid. So how to make this support the grid, rely less on the grid, and being able to connect to reconnect from the grid and work in grid modding and the grid following modes if needed. So in case of any failure from the grid side, disconnection from the grid side can feed those critical loads, let us say critical loads. So managing this system, no doubt the machine learning for managing the batteries, your charging, communicating with the end users to optimize the charging times, the prices, all those kind of stuff is heavily based on AI. So the role of AI is very, very essential in here, although it's very, very, very demanding. So here we speak, we are moving to having those smart devices. Actually, the whole system, the whole components, the whole elements from the device level to unit level to the system level to be smart enough. So speaking and following on the digital twin, we succeeded also to build that on the inverter side and implement with reinforcement learning so that all the controller, so having like controls such as STM 320 dual core, having the digital twin on one core and the controller on another core. So experimentally done and implemented to control the inverter while connected with the grid and supporting to the grid. So those are becoming actually a reality in the application. And what we are trying to do in having a fleet of inverters so that those behave as a shield dome, so that everyone also can monitor itself and the other neighboring DGs. And of course, this can behave as autonomous, self-healing, can connect and disconnect from the whole, and support the whole grid, so that finally you speak about a resilient power grid, which is a target. So this is being done actually at the not only the big, speaking about the big system level, but you are building that from the unit level. So those unit levels are becoming more and more intelligent. So here, moving our traditional grid and making the comparison. So this initially was a comparison done by Dr. Frid Blabjerg from Denmark. And it is about comparing between the traditional grid and our actually the future new grid. And I personally added more in that, looking at the intelligence that is becoming. I would say that the future grid is doable. Although those are big challenges, but AI is an enabling technology here and demonstrating the benefit of artificial intelligence in the power electronics dominated grid is, I would say, is doable. So starting now from the research, of course, more on research than on a reality, but this is coming. And this is the, I would say, the future in the power grid paradigm. Still, I say more intelligence is needed, but there are many functionalities beyond the traditional grid that can be really added. We don't want to mimic the behavior of the old grid, but really we can get more and more. Especially, I appreciate the role of my researchers, former researchers, and a big team behind that, many of the PhD students. I invite you to a conference that we are organizing in Antalya. So it will be a very beautiful place, very nice place in Turkey. So in May. And also for the first time in the region, IECON, which is the flagship conference of industrial electronics, IEEE Industrial Electronics Society, will be organized in Doha. Thank you very much.
Thank you, Dr. Haytham. We have time for a few questions. Yes.
Well, actually, the question is probably broader than just the grid. So the good thing about the data-driven model, is characterizing a process that we don't really understand well. Regardless many parameters, maybe try to do simplification. But when you apply this for a critical control, so the issue that always comes, what if there is a glitch that in the model itself, and the scale. So in a sense, we probably could be achieving something the opposite of what we wanted, or what the objective is. So comes the issue of trust of this, particularly when you apply it on the larger scale. Regardless what you do, is always something that maybe the data that you used initially did not really cover. So how we mitigate with that? What is the risk associated with it?
Yes, of course, this is very, very important question. And I would say what we do actually, this is the lab environment, what we are doing. So whenever we test something, so this should be carried out experimentally. And experimentally, always what you do is putting the extreme conditions. So the worst condition that could happen in terms, whatever, of the loads, of the short circuit, depends on the conditions. So if you impose such kind of thing and you prove that the consequence won't be catastrophic for the grid or the environment or whatever, then you should be okay. Of course, different testing and experimentally. Finally, really, the demonstration is very, very important. When you go for simulation, I agree with you. Finally, what if? Always, actually, Dr. Ghassan today mentioned about the research environment. In many cases, many things are neglected. And then showing in the papers good results is okay for such kind of working environment. But when you go for experimentally, things will appear. And experimental verification that is close to the reality of the commercialized products will say that.
Assalamu alaikum. My question is how to ensure load balancing in decentralized grid using reinforcement learning. How to ensure load balancing in decentralized grid using reinforcement learning?
Actually, the example that we give, the example is about the stability, about specific application. So it depends for what you use the reinforcement learning. So it depends on the application that you are using. But in general, about load balancing in the whole grid. So it is about the whole grid. Those should be smart in monitoring the system. Actually, the power grid relies, so you have the system operator, you have the transmission system operator, you have distribution system operator. So you may have centralized and you may have distributed. Finally, if you speak about a smart unit that is capable of observing the output of the system behavior, this smart unit can identify the need, let us say the need of the active power and reactive power finally, and support for whatever inertia and etc. So observing the behavior of the grid, those smart units can identify the amount of energy that they need to put to the supply. Identify. Prediction is something different and more. So prediction could be for the planning. So you can predict, the system operator can predict or energy forecasting. So that can be planning. So what's being done? Let us say now in our current grid. So you have DGs. Those big DGs, usually they don't operate at the maximum available power. So mostly we speak about maximum power tracking, but in reality with the big, large DGs, they are not allowed. Even the synchronous generator, no synchronous generator is operating at the peak, always around 80%. So always you need to have certain ramping. Always you need to have this kind of curtailment, always. So spinning reserves, you need to have it. In the real systems, also some of those DGs, they work at 50% of their capacity. Because, and they observe, the DGs, they observe the frequency. So lower frequency means that the grid needs more, so they push more. So now with proper forecasting, then those DGs, actually it is market. Now this curtailment is in the market, so who will pay for that? If you don't capture this amount of energy, you lose it. And the storage is very expensive for the power grid. Therefore, the DGs are intelligent enough to identify the way. So more intelligence in the power grid, they would allow the DGs to operate at closer and closer to to the maximum available power. So it is economic for every. It's a win-win.
Thank you, Dr. Haytham. We'll go to the next talk. Thank you. Okay, our next talk is titled The Role of AI in the Energy Transition, and our distinguished speakers is Dr. Aidan O'Sullivan. He's Associate Professor in Energy and AI at University College London. He leads the Energy Systems and AI Lab. He founded the Energy Systems and Data Analytics, and he is having MS programs. He basically established the data analytics program and has a background in mathematics and transport systems from MIT. Join me in welcoming Dr. O'Sullivan.
Thank you very much, and congratulations to the Arabian Journal on Science Engineering for 50 years and all the great progress. Very impressive and really great to be here talking to you. So this talk is going to have some similarities with the previous two. It's more of a zoom out, 20,000 foot kind of overview of the energy transition and the role of AI in this. Give you a little bit of an overview. This is how we'll talk. I'll introduce some of the energy transition, some of the key issues involved and some of the challenges associated with the energy transition, and then talk a bit about the role of digitalization and software in this transition, which is primarily a hardware transition, but software has a role to play as well. And AI being a software technology blends in and supports a lot of this as well. So I'll then talk a bit about the characteristics of AI that make it a good solution for the energy transition, where we can use it, and I'll also talk about some of the applications being researched in my lab. It's not possible for me to enumerate all these solutions, so hopefully in some of the characteristics of AI can inspire people to come up with their own ideas of the role it can play in the energy transition. And then finally, I'll talk a bit about the impact of AI on energy consumption and a little bit of the work that I do with IRCAI, the International Research Centre on AI, where we're trying to find and support good applications of AI for sustainability. So whenever talking about the energy transition, it's important to introduce the trilemma. And essentially what we're trying to do is balance the three legs of this triangle. So how do you get an energy system for your country that is secure, equitable, and sustainable? It's not enough to build the best technology and increase the price of energy massively. That's a little bit like what we've seen in Germany, where the industrial sector is really suffering because of some of the applications of renewable energy, which have driven the price of energy up. Equally, you want a secure supply. You also need people to be able to afford to access energy, given that we depend on energy and electricity now for even things like education. If people can't access or get online, then they can't access their education. So it has to be something that everyone in society has access to energy and the ability to make use of it, and a secure supply, that we're not subject to rolling blackouts and things like this. And again, on the importance of energy, this is a very famous data visualization. And the key thing is that to bear in mind during the energy transition is that there's no such thing as a high-income, low-energy country. So again, lots of countries have made progress along this line, moving up forward in development. It's been a great success over the last decades to see people making this kind of progress. But while we are trying to be more efficient, it's important to acknowledge the role that energy plays in a profitable society. And I'll be talking about the whole energy system, and it's important to keep in mind that when we talk about the energy transition, it's not just about transitioning the grid or transitioning to electric vehicles, it's everything, it's the whole system, and they have all these complex interactions together. So again, this is a Sankey chart of the energy consumption in the US, and you can see the large role played by transportation. Generation feeds into different sectors like the industrial sector, residential, commercial, and there's significant feedback loops and symbiosis here in terms of interactions. So it's a complex system with complex interactions, and a change in one area affects a change in another sector as well. So again, when we talk about the energy transition, we're often talking about hardware. How do we move from fossil fuel consuming hardware to to non-fossil fuel consuming hardware or generation that's renewable. And a lot of the progress that we've seen recently has been in the reduction in cost in these technologies. So significant investment has led to a significant fall in cost. When we kind of model this, or when we look at this, we talk about technology learning rates. So for every time we double the installed capacity, we see a reduction in cost of, say, 34% for solar. So this is great. This is where the kind of progress that's enabled us to drive forward has been coming from. We also see these kind of curves when we look at battery storage technology, and it's very significant for deploying this technology as well. But it's primarily hardware based. And all these kind of different technologies will have different learning rates, but they're also kind of constrained in the fact that they are hardware technologies. So if a new and improved wind turbine is released tomorrow, it doesn't propagate through the entire fleet for 20 years. There's a turnover time, there's a time for adoption. All these things are really difficult objects for us to overcome in the energy transition. Sunk costs, capital investment, these things are challenging for us by the nature of the technology itself. They're limitations of hardware technology. Software, however, is an entirely different paradigm. So digitalization has become a real key part of the energy transition. It really supports and enables it. And we talk about the 3 Ds: decarbonization, digitalization, and decentralization. And these all interact together. So when we think about the solutions we want to drive, or when we want to get to good solutions for the energy transition, we often create new markets to try and enable these solutions. And markets are information and data exchanges fundamentally. So the limitations of the market, the limitations of the software behind it often inform some of the solutions that we see, or some of the behaviors that we get in the sector. So 2 important characteristics that we want to get more of into the energy system are flexibility and visibility. These are key components for the UK's strategy for getting to clean power by 2030. Flexibility, we want to have 4 to 5 times the amount of flexibility we currently have on the grids. Some of this comes from things like vehicle to grid, smart charging, but also actual storage that we're building in terms of battery storage. So this is entirely dependent on digitalization. You need software that allows you to deploy these assets, to use these assets in an efficient, intelligent way, and that means you're not relying on the same paradigm you had before. Equally, visibility is really important. So we're moving to a decentralized system where renewables are located far away from sources of demand. But we also have more smaller generation on site as well. So we want to be able to enable, say, 1 megawatt generators to participate in a grid that's been dominated by 500 megawatt generators. So again, this all increases the complexity of the system as we go forward and leads to challenges in terms of managing it. So when we talk about these learning rates for hardware technologies, if we look at software, it's a completely different paradigm. And what you see with technology adoption in software, GPT was the fastest app to ever get 1 million users, and how we distribute the technology is completely different. I mentioned fleet turnover for wind turbines. If a new improved software is launched tomorrow, it costs nothing for most people to upgrade their current version and deploy and download the software. So the rate of progress that we see in artificial intelligence, the rate of progress that we see in this technology is based on the characteristics of a software technology. And this is really valuable for tackling the energy transition, where we need to make huge progress very quickly. So if we're going to talk about AI, it's helpful to kind of have a working definition. Getting a definition of AI is really challenging, and getting people to agree on what is and what isn't AI always ends up as a bit of an argument. But nowadays, people tend to be using AI as shorthand for generative AI. That's not really correct. AI is a much bigger field than just generative AI. It encompasses machine learning, encompasses lots of control, lots of different technologies as well. But some of the useful paradigms to kind of keep in mind during this talk are things like reinforcement learning. And again, the type of algorithm that we use is determined by the type of problem we're trying to solve. Often the kind of problems we're looking at in the energy system are where we don't have a huge amount of data. We don't have millions and millions of generators. We have a very limited set, for example, versus, say, B2C kind of applications where you have, Facebook, or you have the ability to do online trials or things like this, A/B testing, for example, of a website. You can't really do A/B testing in the energy transition so much. So often we are kind of in a low data regime, and that's why reinforcement learning can be a very powerful method for this space. We're very good at building virtual environments and accurate physical simulations, but we often don't have a huge amount of data. And equally, ensemble-based approaches, I think I've seen one of the posters outside talking about ensembles for photovoltaic forecasting, and ensembles are very useful in this area because of data quality issues. We often have a lot of data quality issues because we're dealing with very messy real-world systems and trying to kind of maximize performance there. And then finally, neural networks and deep learning. Again, this idea of doing kind of feature transformations, letting the model learn those feature transformations, but also this kind of belief in a miracle is something I quite like. So again, the use cases within the energy system all demand a kind of a broad spectrum approaches, broad spectrum of algorithms. And often kind of that dictates where we can deploy and how we can approach it. So another thing to keep in mind is the modality of data. While we've seen kind of lots of progress in large language models and also things like DALI and image generation, a lot of what we're working with are signals from physical systems. We're not necessarily trying to solve a natural language programming issue where being very articulate in language is very helpful. Often we're working with time series data, which has been fairly immune to kind of progress in deep learning so far. And part of this is kind of the challenge of the data itself, and also the links between the fundamental building blocks. Again, I quite like the idea that the Excel spreadsheet might be the last thing to fall to AI. People opening up Excel spreadsheets and using contextual knowledge to understand them is still something that is really important versus kind of report generation or image generation. And this is again because in an image, a pixel is a pixel, no matter what image you're looking at. The fundamental building block is a pixel. In time series or in tabular data, there's a lot of contextual knowledge needed or embedded that you take into it. For example, what did the shorthand headers mean and things like this. So again, the modality of data in the energy system or in the energy transition means we're often looking at kind of applications on the fringes of AI, that things like ChatGPT are not necessarily the best available tool for what we're trying to do. So again, if we try and bring all this together to kind of give a recipe for where AI can play a role in the energy system, the characteristics that it has are this kind of distributed intelligence idea and the speed and scale idea of software. So software diffuses very quickly. There's also very low cost to having multiple users, as opposed to, say, the cost of multiple solar panels or multiple wind turbines. And so this kind of gives a indication as to where it can be used. So we often want applications where we can use the strengths of AI, so constant attention, decision-making speed, to improve the operation of existing infrastructure. And again, a lot of what we're doing is building new infrastructure, which is very capital intensive. And this kind of is a key characteristic of the energy transition. A lot of the arguments for it are that the capital investments that we make now will lead to lower operational expenditure later on, that this is kind of a new way of doing things where we have high upfront costs, but very low operational expenditure where you're not purchasing fuel, for example. So again, the idea is to improve the operation of the system as it is, but also to enable operations that we haven't kind of been able to do before, to do things we've not done before here. So again, looking at the characteristics of AI, one of the problems that we've seen people working on for a very long time is autonomous vehicles. While there's kind of been progress, it's maybe not gone as well as people would like. And one of the key challenges here has been the nature of the problem. It's an open world problem. You want an autonomous vehicle that works in the real world and is able to kind of handle a lot of the irregularities that it experiences, that a normal driver adapts to. So, for example, a pedestrian crossing on a green light isn't supposed to happen, and there may not be a lot of training data for that. So this is the problem of an open world kind of problem. what we have in the, or what we want and what we have in the energy system are closed systems. Again, something like the grid is much better defined than trying to drive a car. The grid doesn't change on a day-to-day basis. The system is very hard to access. During the French Olympics, the operators were sealing the manholes so that nobody could actually go into the system as well. They were welding the manhole shut to make the system entirely separate from access as well. So again, this kind of infrastructure is critical national infrastructure, so it's very sealed off, very well-defined boundaries as well. So again, this is another area where we like AI, the kind of problems where it will be strongly suited to. So this leads me to kind of one of the first applications that we're talking about. This is applying AI for the power grid. And this is research that was deployed as part of a Europe's 2020 challenge and 2021 as well. It's called the Learning to Run a Power Network Challenge. So essentially we created a virtual environment of a grid, and we trained or allowed different companies to compete, different researchers to compete, to train AI agents to manage the grid. And the challenge and the score for the challenge was who could make the grids run the longest without experiencing a blackout. And I think the limit was 36 hours. So essentially, a grid is highly complex, interconnected, as we see with Europe here, where the UK is connected into Norway, into France by interconnectors. And what you have essentially is a system operator who has people in the control room who make decisions on an hourly basis, if not half-hourly basis, that maintain the grid stability. So it can be something like turning on a generator, or it can be something like closing a line or turning off another generator again. So this is getting more and more complex as we add more and more complexity into the system, more and more generators, more and more decisions for people to take. George has talked about some of the problems that you get with adding different types of generation in. But essentially the job is done by humans in a control room, team of 3, team of 5, and the objective was to see if an AI could deliver this as well. So the project was a real success. The environment is still available for people to do more and further research. The winner was the kind of Chinese version of Google, Baidu, who did a lot of simulation using GPUs to kind of win this. And essentially it kind of showed we also learned interesting strategies from the operator that would not have been used in practice or would not have been thought of by a human operator as well, in terms of ways of switching the lines far more frequently than a human operator would do. And this is generally because of the complexity of the problem. It was kind of overwhelming for a human operator to think of doing this as a strategy, to keep opening lines and keep closing lines to change the grid. But it was a viable strategy that led to a really good performance for this AI. So someone asked a question about how you balance the grid using AI. So this is the unit commitment problem. Which generators do you turn on and which generators do you turn off? And you want to kind of do it in the most economical way possible. Again, buying power for the cheapest price and using the cheapest generators available. You also need to keep a little bit of reserve in play. And this is getting more and more complex as we add renewables into the system as well, because they introduce uncertainty into both our demand forecast and our supply forecast. So essentially the idea was to train a AI agent that could decide what generators it would turn on based on a forecast demand. And essentially it learned over millions and millions of simulations that the forecast was often wrong, when it was wrong, how much to keep in reserve, and what kind of strategies to take there as well. So it's a really complex problem. Essentially the decision space grows kind of 2 to the power of generators that you have. So if you have 100 generators in the space, you have 2 to the power of 100 decisions to make, which is highly complex. So you need a lot of symmetry, need a lot of usage of different algorithms. The algorithm that we used was essentially the same one as the AlphaGo algorithm, which is the Monte Carlo tree search. So essentially the agent would make a decision, then roll out further, see what the effect of that decision, sometimes back up the tree, go down a different tree, all to kind of find the best way of scheduling generation in the system. So this was an example of a final solution that it came up with, where different units are committed. For example, purple, I think, is the wind generation, which is kind of trying to maximize out of the available forecast there. So the black line is the actual forecast, and then the purple generation is the actual amount of wind used by the system. So the rest is made up with some base load of various different cheaper units, all kind of aggregated together across the entire system. So this would be a really useful improvement on what we're kind of doing currently. in terms of using optimization routines to do this. But this would the fact that it's an RL agent that's trained means you can do it continuously, updating again and again, versus this kind of one day ahead approach. So lots of improvements can be made there that will really improve the operation of grids. Another piece of work we're looking at that touches on the kind of the keynote speech from earlier on today. Just see how I'm doing for time. Okay. So we've talked a bit about the challenges of being a black box and how this creates problems for us across deployment and understanding what's actually being learned. It's even more so the case in critical national infrastructure. If you try and bring a black box to the control room, they often have a lot of misgivings about using it. So our idea was to take a deep neural network trained by another group and try and understand, using explainable AI approaches, what was actually happening under the hood, trying to understand what was going on. And this was being done to forecast the electricity price in day-ahead markets for 5 different markets across Europe. So we did the whole kind of study across all 5. And essentially some of our results were really interesting in terms of contrast with the more intuitive approach that we would expect. So if you're trying to predict the electricity price tomorrow at 2 p.m., your best guess is usually, as a human, the same price today at 2 p.m. What we saw when we analyzed the inner workings of the neural network, and again, this is time series tabular data, so we're not able to do the analysis using images where we can highlight, regions of interest. Instead, what we're looking at here is the weight of different features for different hours. So what we found that was really strange was it was using the most recent hour's price available to forecast the entire day. And that's completely the opposite of what we would do normally, which is kind of the intuitive price curve matching approach. So this was a really interesting result. It shows a strong preference for recency information. And again, we also see some structure in terms of how it's using renewable generation forecasts, that it's kind of averaging them together to take account of the uncertainty around them as well. So again, we're able to talk more about how a forecast is being generated, which helps get over that obstacle of deploying this in critical infrastructure, where people are reluctant to use something from a black box. So being able to explain how the forecast is made makes it more palatable to an operator as well, which is a big part of getting it used. Predictive maintenance for offshore winds, I won't say much here, but again, this idea of CapEx versus OpEx. 30% of the lifetime costs of a wind farm, particularly an offshore wind farm, are from operations and maintenance, keeping the system running, because whenever you have an issue, you have to send out a boat to offshore to send out repairmen, and it takes kind of 24 hours at least. So again, often availability of wind farms is far reduced by O&M problems. And the the Hack the Wind competition was essentially a machine learning hackathon to develop the best algorithm to predict outages in wind farms, and it was able to kind of predict them 60 days in advance and bring down the availability loss due to maintenance. So again, it's hard to talk about the positives of AI in the energy sector without talking about the energy consumption. It's been really significant point of discussion for quite some time. The training costs for these large language models are really, really significant. Again, the demand for GPUs and the amount that are being deployed, 100,000 GPUs in a data center, means that data centers now are commonly in the 100 megawatt, 200 megawatt scale, if not higher for some hyperscalers. And again, total energy costs for Llama 3 were 30 million GPU hours of training. And again, this is really significant energy impacts. However, there's a lot of uncertainty around this. So while we're seeing massive investment in data centers, this is essentially 4x'd from a baseline of 2019. So it's the amount of investment in data centers in the US, and it's quadrupled in 4 years. And this is having an impact on the grid in places like Virginia, where you have kind of almost 25% of the grid's power consumption is due to data centers. However, the IEA even say there's a huge amount of uncertainty around this because of the improved efficiency. And when you see kind of models like DeepSeek come out that have kind of shown a 50% reduction in the energy consumption used to train the model, also using kind of H800s instead of H100s, it shows that there's a lot of room for improvement. So while we're trying to make forecasts of the energy consumption based on what we're seeing today, it's clear that there's a lot of that can be done in terms of improving the energy consumption of training AI models. And finally, just to wrap up, as part of the UNESCO IRCAI program looking at AI solutions for sustainable development. While there is this kind of issue of energy consumption of AI, we do also want to shine a light on some of the best applications or the most positive applications for society from AI. And we would encourage more people to put projects in. If you're working on a PhD project with potential positive benefits for society using AI, please do submit, particularly anything related to the Sustainable Development Goals. Again, we really want to draw attention to people who are using kind of this technology for really positive applications in the world. And yeah, this is where you can find the project. But yeah, thank you very much. That's all from me.
Thank you, Dr. Sullivan. Any questions? Okay.
Thank you very much. Very interesting talk indeed. I have a question which is not relevant to AI, but your model of triology. In terms of sustainability, we also, talk about the concept of inclusiveness. So where does, this transition to new energy system also contains models and development, and also, of course, the developing the AI technology for energy system that considers the goal of inclusivity, where energy is accessible to each and every member of society.
Thank you. Yeah, it's a really great question. In the UK, for example, net zero is going to come under a lot of pressure given the financial constraints, and kind of justifying net zero is going to be a real big challenge. It was a question put to me recently at the Stats conference, which was, who is net zero for? How do you motivate marginalized communities or less well-off communities that this is something that investment should be going into? And winning that argument is really important, and kind of making sure that everyone is on board with that to maintain support for something that is going to cost a lot of money in terms of upfront investment. The big kind of, well, again, from the UK, energy security is a big part of that discussion. Not many people remember, but in 2022, a lot of energy suppliers were put out of business. They went bust because they weren't properly hedged and gas prices exploded. So the UK consumer bore the cost of that. So again, a lot of government money was spent on bailing out these companies. That ultimately means money was taken out of the public purse. So some of the ways of justifying it come back to energy security, as much as it does kind of the climate emissions argument. People don't feel climate emissions as much as they kind of feel energy prices, and that's kind of the challenge of the argument that we have. So yeah, it's going to be an ongoing debate for a long time, I think. Must be close to lunch.
Okay, thank you all for joining us in this session. Thank you. So we'll have a
welcome everyone. Welcome back to the new session. طيب. Assalamu alaikum. Bismillah. So today we have our first speaker will be Dr. Ansar Yasser from University of Hasselt. He is working in the IMOB research group. Professor Ansar is a professor specialized in smart cities and autonomous mobility. He has published, mashallah, many papers, over 200, I guess, journal papers, conference papers, and he contributed to many global transportation initiatives. Today, inshallah, he will present AI and electrification, shaping autonomous mobility for cognitive and sustainable cities. We are looking for your presentation, Dr. Ansar. You can start.
Thank you, Dr. Ahmed. It was, thank you so much. Thank you for the kind introduction, Dr. Ahmed. Assalamu alaikum. I have to appreciate the KFUPM's media team I was also surprised to see my old photo still having more hair on my head than I have now. This is the second last presentation of the day, so I promise I would try to keep it alive also for my own self. So I'm enthusiastic when I try to speak, and I'll try to keep that enthusiasm in line. So my talk is a little bit in line with my colleagues who spoke earlier, although my focus is not on the electrification part. So while grid is very important, but my focus is not primarily on the grid, but my focus is primarily on the systems and services associated with the grid. So for example, like mobility and other smart city applications. So my presentation will also be based in several parts. So I'm going to talk a little bit about electrification goals. Why are we interested in electrification? Also focusing how can we make it happen with the use of AI and other associated technologies. We'll definitely talk about autonomous mobility because some of my colleagues also talked about it, and I think mobility is a vital part of everyday's life, and it has also a very important impact on the consumption and other demand patterns that we see every day. Then the big question is, for some of us at least, I think in the morning, Dr. Manal talked about the EU's AI Act, and in that act also they ask themselves the question, is AI the problem or not? We'll see. And I'm going to propose some frameworks to implementation and some call to actions and future outlook, especially also with regard to the Saudi and GCC environments in general, because we have also a shift from more traditional economies to more digital economies in this sector as well. Starting off, net zero CO2 emissions, it's a big wish list. Everybody hopes that we reach that, at least used to hope that we'll reach it by 2050. According to IEA, the Paris Accord, and the goal was to have it by 2050. But low international cooperation, and I don't need to name the countries who are not cooperating very well, also led this to now be extended by another 40 years. And I don't need to explain you the reasons of why we need net zero, but I will try to explain how can we still do it, or how can we still reduce this extended timeline by making it a little bit more realistic. So we have to, in order to do that, we have to look into a number of factors. Renewables, of course, some of you talked about it, and we still have a lot of belief in the renewables these days. We have bioenergy, another very important segment that we need to focus on. Energy efficiency, so of course, not every time it's possible to invest in new and more expensive technologies. We have to have carbon capture, which is also very important. Have to have also a focus on hydrogen fuel. And for me, one of the most important one is the behavioral change. Because in order to understand net zero emissions, or why are these emissions there, we have to understand the factors behind. And my belief, and some of you may disagree with me, that I think the human factors are the highest contributors in one of these things. So we have to have behavioral changes
And I think COVID, while it had a lot of negative impact in our lives, but it brought one thing to our knowledge is this: yes, a lot of the activities that we do can be done by not even going to those things physically, right? And of course, electrification. So electrification will be also a core part of my talk, and we'll be focusing around it. So there is a demand in growth of electrification. Why? Because we are recovering from different economic issues or socioeconomic issues. We have also sector electrification in terms of requirements of more data centers. We talked about data centers and how big they are, how vital they are in order to make everything successful. We have also digital expansion, focusing on more data centers for AI and cryptocurrencies and associated things. We have also surge of electric vehicles and AI demand altogether, which may surprise you. By according to World Energy Outlook, you can see that we have almost 6,760 terawatt hour demand in terms of extra surge of EV and AI in terms of this demand. But where do we fit within the overall electricity demand? So if we see into some of the big countries that are consumers of they have huge power demand, so they have advanced economies and some of them not so advanced economies. According to the data readiness report from IEA from 2024, you can see that electricity demands have, if I go back because the slide jumped, they have increased from 27,500 terawatt to almost 30,000 terawatt hour, which is a huge jump from 2022 to 2026. And this demand is even growing further, which is almost an increase of 40% in the next 10 years, that will, or maybe more, because of course some of my colleagues said predictions are not so accurate. According to the current demand and requirements, around those demands we see this demand even growing further. But what are the bottlenecks? Why can't we do it? And I think some of you already mentioned this before, I think very wisely, because I'm not an expert in energy or smart grids, but I am an expert in mobility and smart cities, and I'm associated requirements from those, from the grids to these associated services. So grid constraints is a big thing, because in modern economies, most of the grids that we have are almost 20 years old, and some of the developing countries or underdeveloped countries could be 40 or more than 40 years old. So it is aging. Modernization requires a lot of money. I mean billions. So I'm not going to quantify a number, but that is a problem in terms of modernization. Then we have transmission bottlenecks because of this emerging new microgrid structures, solar systems, wind farms, and so on and so forth. Electric vehicles are also one of the contributors. But this all requires investment. And investment, if we already look at the Bloomberg figures, from 2023 to 2030, the requirement based on our demand is going to close to $0.8 trillion, and as compared to now, where we are only looking at around $400 million, a big gap of about still $500 million is there because of the lack of investments. And electric vehicle sales are also increasing, which I think we can see China, Europe, United States, Japan, India, and other. Globally, they are not so much so focused. But I can say something about Europe because they are really keen to change their economy, especially for transportation sector, for private transportation sector, for completely internal combustion engine-free economy. So where you can see already that in 2030, we will already have, from 2023, we will have a surge of about 40 million electric vehicles. And if I go a little bit further in the future, about 100 million electric vehicles, they simply jump. So and if this demand, I ask myself a question: can the current infrastructure or even the future infrastructure handle this much induced demand? Can we replace what we have already, our traditional engine, gas guzzling vehicles, into all electric vehicles? That's the big question, right? We have to see this, and this is a real problem. And you can see what we will have at the moment. We have to look into the charging capacity as well that we have from 2023 and going towards the near future. In 2023, we have about 0.3 terawatt requirement. In 2030, this goes already 8 times more. And by the time which we look into a little bit more towards the future, we are looking at a 15%, almost 4.4 terawatt demand because of the surge in simply shifting from our current mode of mobility to electric mobility. Do we have that power? Can our grid serve that amount of electricity? Because simply the current simple answer should be, of course, we will fry the grid. But are we willing to have that, let that happen, or would you like to do something else to make it better? So how to tackle this? I think first thing we need to think about is how do we optimize it further by using AI. AI implemented with our current electricity needs base makes grid smarter. How can we make it smarter? My colleague gave a very good example before where they talked about creating microgrids, integrating all these sub-energy systems into one, and in a nice optimized way where we can create this demand responsive system. We can merge it with load balancing and AI and come up with a nice supply and demand parameter. So in electrification domain, we have other things to yet think about because some of you also mentioned problems with energy storage systems, which is very right. Energy storage is not cheap. We look at the technologies for today. For example, lithium. Lithium is also expensive. Production is complicated. Mobility is complicated. Depending on also the resources are limited. But why is that so? It's because is lithium the only possibility for us to, or the only material for us to use this so far? The answer is yes, but the answer is also no, because we don't know the answer exactly. The reason being is because the process where we can discover new materials has been so slow. It took, like, for example, years and years and years of materials research, also validation studies where we could discover, for example, 48,000 materials as compared to what we can do with induced improvement in terms of how can we do that. And Google was very rightly invested in this, where they had this deep mind graph network, so genome systems model, where we had this first problem, traditional approach, a lot of research, a lot of revisioning. Of course, lessons learned, data stored. The new database-driven approach where we can have already existing problems available. We can have already candidate graphs that we have already made. We can already correlate ourselves with what we have done before, new. And this genome model already can come up with much faster materials. So you can already see an increase from 48,000 materials discovered to 400,000 materials discovered for potential research in different sectors. I already said the numbers before. But of course, for electrification, means new photovoltaic material, new battery cell material, new storage systems. And this has a huge increase in a couple of years, just from 2022 to 2024 with the use of genome, much faster discoveries of materials. So it's all thanks to data analytics, deep learning, LLMs, and so on and so forth. Many models were used behind this. And why do we need this? Because the first problem we had the problem about availability of power. Then we had a problem about storage of power. Then we can also see that we have problems with inefficient real-time demand management. So everybody wants to work at the same hours approximately. Everybody would like to go to charge their vehicles at the same time. Everybody is more or less having same lunch hours. Less flexibility with a little bit margin. Of course, scalability is another challenge. Growth in population, growth in demand, growth in number of vehicles, growth in demand of other things, and lack of transparency and trust. Because this is an issue, I will not talk so much about it, but it is a real issue where we do not, we always have an issue with the concerns with availability of the resources to a certain extent. Then we have data privacy. Am I willing to charge my car or my vehicle or supply electricity from my vehicle, just as an example, at any moment of the time to anybody around me? Is this private enough? Because from electricity patterns or your utility patterns of electricity, we can already judge so many things about you. When are you home? How many people are home? How many instruments you're using? Approximation. Although we live in an era where we are sharing data whether willingly or unwillingly, but we are contributing to this big world of data. We are using that data to do a lot of estimations, but there are privacy concerns. So do we need to have that data around us? Can we do something about it? And of course, peak demand stress. So when there is too much demand, and some of you mentioned, we have no ability to meet the demand. So what we can do, we cannot invest in new grids. We don't have $800 billion or $1 trillion to invest in new infrastructure. What we can do, we can try to manage current infrastructure, manage our behavior, change our behavior. And how can we change our behavior, change our activities? Just to start off with an example, where we can say, okay, flexible working hours, or only charge what you need. And how do we know that? By making a complete model around your usage patterns. So this demand responsive load balancing AI framework, what it requires a lot of analytics about you, about charging availability, about demand. So of course you need to capture data about production and consumption, aggregate that in a system thing, do some analysis on this, do some real-time demand management, because of course your system, your patterns change slightly based on other external factors that we may or may not know, and have a feedback loop to improve that model, to retrain that model, and give that as an output in order to have a best case scenario where you have an optimized situation in front of you. Moving forward, what we have at the moment is highly scalable. What we propose as a demand response system, it is decentralized, blockchain, of course, more secure. We can all work and control the supply and demand in each smaller segment of the population. It is more predictive, it is more real-time, AI-based, and transparent as compared to what we had before, where system was still more centralized, limited scalability, and we all know about the issues. And of course, limited visibility to stakeholders, because it's always difficult. This is a very close group that doesn't like changes so much. So I give you an example of a project that we did a while ago. It was a big European project where I was one of the principal investigators, and it was a project called DataSim, and we looked at problems of moving from the internal combustion engines to electric vehicles. Is this possible? Because among the other factors that we measured, one of the biggest factors was range anxiety, which is always there with you guys as well. Can I make it to finish my day? If I start my day in the morning, can I finish it? But how did we do it? This is just for a very high-level explanation for the sake of explanation. What we did, we tried to look into your behavioral patterns. So I mentioned behavior before. What I did, we modeled your activities during the day, so your travel activities or your other activities, based on a timeline. So you can, I don't have a pointer here, but you can see a timeline on the left-hand side. We see an electric battery for a classical car. We have an internal combustion engine availability range available to us. And we did a comparative analysis of scenario 1, scenario 2, taking into account charging availabilities, emission statuses, your travel patterns, and all the required activities, fixed activities. For example, work, less flexible. Going to school, less flexible. Shopping, more flexible. Gym activity, maybe more flexible. So, and we mapped this, we'd run this scenario several times. Of course, we created these agents, microsimulation agents. And these agents were able to do different factor changes, so characteristic changes. And each of these changes reflected a different output to show how can you do your activities, and if this is even possible. And the study area for us to do this project was in a Dutch-speaking area of Belgium, Flanders, with a population of 7 million people. And we already found that all these activities that we model, shopping, at work, at home activities, with, of course, some peak shaving, because if everybody charges at the same time, it's much more difficult. So it was possible to do, because what we could we saw that even with optimized charging and spread out charging, spread out activities, it was possible to do. Another way to mitigate this risk was to also use, of course, we did some AI-based approach for mitigating this range anxiety, where we use this Hungarian matching algorithm. to check different scenarios and run them on a number of parameters. It is basically just to be able to run these scenarios a million number of times, for example, to see what all possible combinations. So moving on, basically we have a lot of private autonomous vehicles. We have no car ownership, because if we shift only from internal combustion engines to electric vehicles, we still have no change in the number of cars that we have. So no effect on mobility of people who cannot afford. We still have more traffic. We still have more unsustainability. A better approach should have been where these systems could only feed based on an induced demand. We know when people travel, to where people travel, to create these smaller feeder lines that feed into a higher or a level public transportation network that is better supply and meet all your travel demands. So we did another case study for electric vehicles. We are part of a project where this is, of course, an example from New York. I will show you the example from Belgium. Something similar we use these electric vehicles for shared mobility. So you eliminate the ownership requirement. And if this electric mobility becomes even autonomous, you even remove the requirement of a driver and ownership. And from that, to start off with projects in US and California like robotaxis, Waymos of the day, we moved to other projects like Show, where we use this for shuttles and mid-size transportation. Implementation was done in different parts of the world, including one in Belgium in a nature park, where these shuttles used to give you a good number of mobility, combined exclusive mobility as a whole. And this was also on top of that. What we did, we looked into other modes of mobility as well. For example, drones, how can they help? Because they are part of your mobility mix. This is multimodality. We always have to look into different number of modes. And we have to see how can we do that. This is not our own video. This is a video from a project where they did small-scale drones, electrified drones, to inspection of electrification scenarios. Moving on, they can do scenarios like with hypothermal sensors, scenarios like firefighting, scenarios like infrastructure and investigation in different environmental and weather scenario sessions. Something we did also for a school approach, which also helped us map out potential problems, was a project that we did in a city close to Hasselt. And what we did was we did traffic analysis, speed analysis. We created this braking behavior analysis with real-time video feedback from the cars. Of course, thanks to AI, we did YOLO. On top of that, we had deep sort. Deep sort actually helped us with this motion trajectories. And of course, Kalman filtering was done, and so on and so forth. To a combination with Hungarian algorithm, we come up with a very nice way of monitoring not only the current activities, but predict conflicts and near conflicts, but also see the potential of things like, what if we change it to electrified mobility? What will happen to noise pollution? What will happen to our demand? What happens to these micro-mobility modes that are very fast, very unsafe? So this was done in a real project for the government where we did this analysis. And this helps for a different number of things. I'm not going to go into the YOLO because this was explained before. We use different versions from version 4 to version 5, combination with deep sort. And what we did was we tried to see peak hotspot analysis with charging points and see how can we meet that demand by optimizing what we have already for us. So of course, critical infrastructure monitoring was also done with a swarm of drones, which I show you a video, which we already had a project where we did this as a whole. All these drones worked as a group of drones and worked as a swarm and get the same data much faster real time. Methods for fault detection, of course, YOLO did it, some examples here, where we can see where we trained this model several times to do simplistic tasks in combination with some cloud services to do this more preemptively, so we can do this completely much faster. Of course, AI is very power hungry. It requires more and more power. We already mentioned about the requirements. So while we are relying on AI, we are creating induced demand for more electricity. So we have to look into this as well. And AI workloads are already quite high. I don't need to mention it again because some of my friends already mentioned it before, actually several times, so this is an important factor. But Google DeepMind is very important. I'm just going to close my slides now, but just to mention that Google also played a very vital role here where we use DeepMind-based smart centers, because data centers produce a lot of heat, requires a lot of cooling. But this demand is not always the same. So what they did, they learned about this demand. They did a multi-layer approach. They did an optimal AI-based action, and they only controlled the heating and cooling based on the required demand, and also some predictive demand as well. So it's not always the same, but it was moving all across the day, all across the week, all across the month. So this is an approach where they can save 30% on energy by just simply using AI on usage patterns. So what my suggestions will be to close my talk, we need to focus more on harnessing AI's power in the mobility sector. We need to look into grid optimization with AI. We need to look at the workforce development. We need to train more people, because also Professor Sam in the morning talked about his scare about the new education, impact on education, and this is very true. We need to balance these energies. We need to also support the regulations, making it happen. We need to have more R&D, of course. Data governance and standardizations are required, and into other utilities, integrations would be required. So just to call of action, more funding, more focus on AI, collaborative approach is the approach to go for it. And something to look for, last slide, is agnetic AI for electrification. I think Professor Stefan will be talking about agnetic AI. It's more into agent-based AI. Each agent would have an LLM, would be able to do different tasks in different set of sectors that we focus on. And I think this is the future to look into. Thank you so much. Thank you for the attention.
Thank you very much, Professor Amsal. We can have a couple of questions. Any question?
Oh, I'm afraid of this question.
Thank you, Dr. Ansar. Have you considered collaboration between like drones and cars, and where do we place the artificial intelligence part on this?
Yes. We worked actually we worked on two projects. Both were of emergency response scenario nature. So we did a project called, it was a project about emergency response situations. There were 18 countries from Europe involved with it. So we had a collaboration of drones and other modes of mobility, not only cars, to also not only help with route planning, but identification of risk, task planning, even using the other vehicles as a mode of recharging electric drones. Because when I talk about drones, we focus only on electrified drones, because if you talk about big drones, they're difficult to handle, there are legislative issues, but smaller drones don't have it. And this coordination is important because each mode of transport, for example, car has a different field of view, a drone has a different field of view, different spatial view as well. And these views combined with each other give a better outlook towards each of these mode of mobility.
And decision making is at what end?
Decision making is based also, each of these entities act independently. There always is a mission-based approach. Always a goal. A goal could be search and rescue, putting out a fire, helping out with finding lively signs. For example, I've told you this was done in a very specific scenario. And that goal was achieved together until the goal was not achieved. There were more drones deployed, different drones with different sensors deployed, different vehicles with different sensors deployed. And this was done completely autonomously.
Okay, thank you.
Hi, thank you for the great presentation. Question about autonomous electric vehicles. Do you see them as going to be competing with public transport? Or are they a solution to the kind of massive transition we need to replace every ICE with an EV? Do you think we'll be able to get away with far fewer EVs, or is it just purely a public transport, people will still want to own their own car?
It's a very interesting question. And I think it requires a very long answer, but I'm trying to minimize it as much as possible. If I look at the current outlook, they are just adding on to the current problems of transportation that we have. Because at the moment, even if you are on the TRL level 7 or even automation level 4 or 5, the problem we have is that they're not tested well enough. Although they have driven more billion kilometers than even traditional vehicles in simulation, combination with real world examples, the lack of trust is creating a problem. So at the moment, they're add-on to the current mode of transports we have. But what we wish for is not only autonomous vehicles. Autonomous vehicles should be part of the mix. Actually, all of these systems, the only solution that we have is looking towards something like mobility as a service, rather than you owning a mode of mobility. That is the only way to solve this. And once they become a combination, for example, feeder lines to feed into big train stations, shuttles, main rail lines or airplanes, only then we would be able to have reduced impact on transportation network. And this can only be done in a very smart way. We need to do planning, we need to do analysis of the current data, huge amount of mobility data, in order to come up with the right choices.
Thank you.
Our next speaker for the session today will be Professor Shahid Tanvir. He has, mashallah, very long experience, over 30 years of experience in innovative urban solutions, focusing on cognitive safe cities, digital governance, multimodal mobility, AI-driven smart systems, and sustainability for an urban environment. Professor Shahid, the floor is yours.
Alhamdulillah wa salatu wa salam ala Rasulullah. First of all, I'm not a professor. I'm a student, and once a student, you're always a student. You learn a lot every day. And I was talking to my good brother and friend from the old KFUPM days that when you teach, you prepare. And when you prepare, you learn. And when you deliver the course, you learn again when the students ask tough questions. And when you try and give an answer, you learn again, right? So learning is a process. Once you start, we always keep learning. So thank you, KFUPM. Thank you, Dr. Bassam, Brother Masood Al-Hassan. Thank you for having me here. I have been going through a lot of emotions, having the opportunity to be able to visit the university after a long time, basically speaking in the university probably after 27 years. So thank you again. Before I start, I just wanted to share a story. Brother Hussam, he was talking about the shake-up of the world by DeepSeek when he was actually exiting from Canada. In my situation, I was entering Canada and I was sharing this with him. And when I landed just about 10 days back, it was snowing heavily. And a good friend of mine, after I reached my hotel, he picked me up and he took me to his home, and he was driving an autonomous vehicle. I will not name the brand because I'm not a big fan. So I noticed that he was not touching the wheels. Literally, it was driving on its own. And after a moment, I realized, and I asked him, and being a techie, he is so into the technology, he has full trust. And he was, in fact, trying to tell me that imagine your son, who is 18, starts to drive, and slowly you realize that he's picking up and he is doing a good job. Why would you not trust your son? And so therefore, the algorithms have improved over the years, and now not just me, when my wife is driving it without putting our wheels, hands on the wheels, and so we believe that is doing a good job. Interesting enough, despite all of my doubts, the vehicle did a pretty good job of navigating, especially, I think Dr. Ala is here, and he knows a lot about the autonomous vehicles and the Canadian environment, where turning left is very tricky, and the vehicle did a pretty good job navigating around the snow as well. So I had to change my opinion about how much technology has improved over the years. So this is brief about my journey. I started from India, was here at College of Computer Science and Engineering back in 1992, left in 97, worked briefly at the IT Center, then worked in North America, briefly in India, and then in government of Dubai for close to 13 years, focusing on the sustainable urban mobility, smart cities, etc. And this is my second innings, as they say in the world of cricket, working for Royal Commission for Riyadh City in the smart cities. So when we talk about cities, we realize that cities are turning into economic powerhouses, and the economy of countries is actually shaped by the cities. Now, at the same time, we are facing a lot of urban challenges. As more and more people move to the cities, we realize that it's a question of demand and supply. There are a lot of resources that we have to share, especially air, water, food, housing, etc. And the number of people moving to the city, it's expected that by 2050, close to 70% of the population is moving to cities. There are a lot of challenges that we face for people who are in the campus and who do not need to often go out. You are very lucky here, because when I first moved out of the campus, I realized what is the real life looks like, right? Where you not only have to worry about moving from point A to point B, you have to worry about the parking, you have to worry about paying your bills, electricity bills, right? You have to worry about water, other utilities, and so on. And so I've always looked at some of my friends who have stayed back in the university, and I realized that they probably do not recognize or appreciate what comforts are offered in a campus-based housing such as this. So there are three major areas that create the highest number of carbon footprint. One is buildings, the other is energy, and third one is transport. The advantage of being the last speaker for the day is that quite a few has been spoken about many areas such as energy, smart urban mobility, and also, there are many things that have been said. Sister Manal talked about the Vision 2030. She also talked about the digital transformation that is happening around us and the kingdom. I mean, it's quite impressive. If you travel around the globe, you realize the ease with which you're able to get the governmental services in the kingdom and of course in other parts of the Gulf as compared to many of the most developed countries. And I think that divide we saw more so during the COVID time, where the countries that were so-called developed countries did not do very well in the COVID. And I think the kingdom, with the kind of leadership and also the technological footprint, was able to manage it in a much better way. We saw the floods in Dubai, something totally unforeseen. We see fires in LA. A lot of devastation caused by the climate disasters in US alone, and I was pretty shocked looking at this slide. More than close to 27 such disasters, which are $1 billion in terms of its impact. Now, one thing we noticed is that during COVID, I just talked about it, we realized that the traffic congestion before and after in a lot of the European cities and also many other cities across the globe, it reduced. We look at the air pollution and also energy use, that also reduced. So the problem of cities is actually related to the demand and supply to a large extent. So if you do not visit your highways during the peak rush hours, the infrastructure is there. But as more and more people come to the cities and they drive around, the same infrastructure is not sufficient enough, right? And so what we require is policies, rules, and regulations. Because without policies, rules, and regulations, if we allow our cities to grow, then no amount of infrastructure will be sufficient. And I have seen in the last 20 years, people usually ask, a lot of investment has been made in traffic and transport infrastructure. How come you started with these technological investments, but then the traffic has increased? Well, you did not control the number of cars. You did not regulate how you are allowing, the proliferation of and the sprawl, urban sprawl, right? The Sustainable Development Goals that are total 17 from the United Nations, one goal focuses on sustainable cities and communities. And the human-centered cities focuses more on people. And when we say sustainability, we are talking about the economic sustainability, we are talking about financial sustainability, environment, culture, and so on. So there are many definitions. There is no one specific definition on smart cities. And most of these definitions basically focus on how we can optimize the resources. How do we make sure that what we have inherited, we utilize them and we leave it for the future generation as well. Now, there's a lot of conversation around smart cities and the evolution of smart cities into cognitive cities. And one area we realize that, many decades ago, we were very happy with offline data. And then after some years, we said we need to have near real time. And now that we have access to the real-time data, we realize that real-time data is also quite late. Because if something has already happened, then the only option I have is to react to it, right? So what we are looking for now is being proactive, right? And so from the Internet of Things, what we need is actually Internet of Agents. And in the agentic AI, this is where the real power of technology is, where things happen and they inform us in advance so that we are able to plan better and prevent urban issues before they occur, such as traffic congestion, energy outages, climate disasters, and so on. In terms of the quality of life, what is it that people want? So first and foremost, safety, time for family and social life. We're talking about our own health, environment, connectivity, jobs, and cost of living. Now, Industrial Revolution 5.0, Industry 5.0, 4.0, and also Fourth Industrial Revolution, they focus on the innovations which allow us to improve the quality of life and livability. Especially Industry 5.0 focuses on welfare and well-being of people more than the people and planet, or prioritizes people and planet over the profits. There are many of these technologies that are able to consume a lot of the data, and it is estimated that the amount of data that was created over the next 3 years will be much more than what we did in the last 30 years. So there are many of these innovative technologies and solutions. I would actually request extra 5 minutes, if you don't mind, because there's a lot of content that I have to cover. So I'll quickly go over some of these slides. So there are many of these innovative smart city applications, and the purpose of this is to make life better for people. There are examples from the kingdom. Tawakkalna, which started as a tracing app, and now it has become a kind of a super app at the national level, also focusing on Riyadh City, for example, integrating a lot of the governmental services. We are talking about a new parking app, which will be launched soon, helping people find the parking in Riyadh City. There are a lot of applications that have been developed in the last 10 plus years in Dubai, for example, where a lot of innovative ideas, including UAE Pass, that allows you to use your identity across the governmental entities. We are talking about the various benefits of smart cities that are very, very clear in terms of the economic impact, in terms of the impact to the GDP, also creating new businesses from the data that are shared by the cities. There are some very good examples of London as a leading smart city, where they have focused on economy, people, and the governance. We are also another good example of a smart cities is Singapore, that has a Smart Nation program, and they have actually extended it to Nation 2.0, where again the idea is to focus on the social well-being, sustainability, and governance. And finally, the example of Dubai, where it started with the vision of the happiest city on earth, and it has been able to deliver a lot of the services. The impact, the vision of Riyadh City, as we can see, is focusing on the data-driven digital technologies with the objective of making the city more safer, livable, connected, and so on for all kinds of stakeholders of the city. There is also Riyadh strategy that focuses on the renewable energy. It focuses on the adoption of electric vehicles and the greening of the Riyadh city. And then you see that a number of areas and the communities within Riyadh has benefited from this. The recent example is the world-class metro infrastructure that has gone live, and it is impacting the residents and visitors of Riyadh city. You see these colorful pictures showing inclusivity, where people across the demographics are coming and benefiting and enjoying. Now, when we talk about buildings, obviously cities cannot be made smarter without transformation of the built environment. And so in this context, buildings play an important role. That's where we spend 90% of our lives. And there are many, many areas, indoor air quality, personalized HVAC, health and well-being of people who are inside the buildings. Technology has a big role to play. Within the cities, there are many districts, and these districts are mixed-use communities that focus on the principle of allowing people to live, work, play, learn, shop, dine, and socialize. And this is an example of Dubai sustainable city. And the idea is that young families where they need to interact with each other, and rather than giving them big houses, they are made to go out and spend time with their neighbors. And they also have biodomes so that you can grow your own plants, especially day-to-day, that can fulfill your day-to-day needs. They have solar energy, and they basically generate enough energy to be able to support the community center. And there are a lot of activities that they're provided. And the whole idea is, how do you improve livability by injecting these ideas around community and the ability to interact with people, rather than disconnect from each other. So these are just some examples of AI, where AI is used in the metro system for peak scheduling, so that you could optimize the resources and utilize them better. In Riyadh city, mobility, especially within the public transport, more than 10,000 CCTV cameras. They provide the safety and security utilizing Sadaya's Smart C platform. We are talking about the Riyadh Operations Center, which helps in consolidating data from various platforms that exist, such as safety and security, transportation, etc., in order to manage large events. For example, LEAP and Biban were the two events that were managed around 2023. We are talking about the autonomous shuttle services to serve and integrate well with the existing mode of public transport as first and last mile, rather than the replacement of public transport. There are also predictive policing solutions, disaster and crisis management solutions, where AI is very, very helpful. And a lot of these have already been covered, so I will quickly go through this. These are just some pictures from Dubai, digital twin use cases. We are talking about multiple examples of digital twins in the smart city context, where they are used for managing the urban mobility and traffic flow, human flow, sustainability. We are talking about firefighting, emergency and disaster response. And there are other examples as well where our digital twin is used to improve livability, urban planning, improvement of the heritage buildings, studying ancient sites, and also the improving spaces and human flow. And last but not the least, these are some examples of blockchain that were initiated in Dubai back in 2015-16, where it has been applied to solve urban challenges across different domains such as transportation, safety, security, budgeting, taxation, etc., and especially around the business registry blockchain by the Department of Economy. There are other examples as well, and I think some of these were already covered in the earlier presentations. That's it. Thank you very much.
Thank you so much. Jazakallah khair. Very interesting presentation and very informative one. I have actually two concerns about this sort of transformation of the electrification. Do you have any sort of like statistical studies about the potential infrastructure in regard to the electricity grid, comparing to the load or the potential load for increasing number of EVs, considering, of course, increasing number of homes, people, So do you think the potential infrastructure for long term, for next, let's say, 5-10 years, is going to be sufficient for this sort of pushing for the having this sort of autonomous vehicle or EV? And so do you think we are ready for the next, let's say, at this stage, for example, for the normal situation, we have like many cut-off in many countries in the electricity. So do you think the potential infrastructure is fair enough to handle this sort of transformation?
I think this question was better suited to Dr. Yasser, because I think he touched upon it as part of his presentation. And I'm not an expert of the smart grids or energy sector. Predominantly, we are focusing on how do we use the existing infrastructure that is available or the new technologies that are available to provide services to people within the context of smart or cognitive cities, right?
Yes.
So, and I think it would be a good academic question to look at and kind of address from the R&D perspective. I couldn't understand, from a smart city perspective, we don't look at the capacity of the infrastructure, for example, right? Because this is a question that needs to be studied and taken a deep dive from the energy sector perspective. Whereas us as people involved in smart cities, we try and talk about digital services and innovative services, like in terms of mobility. Dr. Yasser talked about mobility as a service. And, across the globe, there is a new trend where they're talking about injecting the mobility within existing, let's say, service providers, mobility as a feature, right? So these are some of the innovative ideas that we explore. But to answer your question, this is not something that is my area of my expertise. Yeah.
Second, just very quick concern regarding the pollution, because when you're talking about EVs, the first advantage for EV saying, we reducing CO2, emissions for, in the year. However, still for EV batteries, we have very negative impact on the pollution as well. So for long term, I'm talking about long term, next like 10 years, do you think at a specific stage, we're gonna complain again saying, look, we did some mistakes about, pushing too much in this sort of transformation, and we have to look back to, adjust the things. So that is my concern.
Yeah. So again, my answer would be we are not in particular focusing on autonomous vehicle or electric vehicles, right? It's also where the world is headed, right? So when everybody is talking about electric vehicles, when everybody is talking about autonomous vehicles, we have to explore these technologies. And I think it's quite unpredictable at this time, as Professor Yasser said. Do we have the answer to the question? The answer is yes and no. The answer is we don't know, right? So this is my answer as well. And I think the focus of my talk was not on EV or or on the autonomous vehicles. The focus was how do we make cities more people-centric so that at the end of the day, when we talk about cities, without people, there are no cities, right? And so therefore, just promoting technology for the sake of technology is not going to help us. Unfortunately, these days, what we notice is that more and more innovation is disconnecting the people from each other, right? So in the name of social media, we are becoming antisocial, such that when we are in a room like this, we are not talking and interacting with each other, but we are happy to talk to or interact with people who are far away, right? And so what this is leading to, and I'm being a little bit philosophical, is that this is causing a lot of the mental problems, heartaches, and stresses, because by nature, human beings, when we interact with each other, there is a kind of peace and sanity that we get out of this, right? So focusing technology for the sake of technology and making people just live for the sake of technology, I think it's not really ideal. And therefore, newer models of a smart city focuses on enabling people and empowering people through technology such that they will have more time for themselves and for their families, right? So the idea is if I save time in traffic congestion, right? If I can avoid traffic congestion, the amount of time that I get, I should be able to focus it on myself and interact with my families. So that's where the smart cities really contribute in solving the urban challenges and making sure that I have a more fulfilling life, and everybody has a fulfilling life in the city as well. Thank you.
Thank you. We would like to thank all the speakers today and also all the attendees. Inshallah, we hope to see you tomorrow with engaging discussions and questions and so on. Assalamu alaikum wa rahmatullahi wa barakatuh. See you all tomorrow, inshallah.